the Atlantic Ocean is shifting. Right now, the Gulf Stream, the warm current that keeps London above freezing and feeds rain to half the planet, has drifted 80 miles north of where it sat 30 years ago. Forecasters are watching satellite data with growing alarm. Beneath it, a hidden river of cold water is weakening. Ahead, you'll see the exact tripwire scientists discovered, the cities that could plunge to -40 in winter, and the tipping point that may already be behind us. Hit subscribe if oceans and climate fascinate you. Prepare yourselves. We begin. Off the coast of North Carolina, near a sandy spit of land called Cape Hatteras, something massive is happening beneath the waves. The Gulf Stream, a river of warm water hundreds of miles wide, has moved. It has drifted 80 miles north of the path it followed 30 years ago, and forecasters watching the satellite data are no longer calling this normal. For decades, the Gulf Stream has been the most reliable feature of the North Atlantic. It curls up from the Gulf of Mexico, hugs the eastern coast of the United States, and then peels away from the shore right around Cape Hatteras. That peel-off point is the heartbeat of the entire system. It is where billions of gallons of warm tropical water turn east, head across the ocean, and deliver heat to Europe. That heartbeat has shifted. A study published in early 2026 in the journal Communications, Earth and Environment used satellite altimetry, basically lasers measuring sea surface height from orbit, to track the Gulf Stream's path between 1993 and 2024. The result was unmistakable. The current is migrating north, slowly at first, then with sudden bursts. Underwater temperature sensors going back to 1965 confirmed the same thing. This is not noise. This is a trend with statistical fingerprints all over it. Imagine a giant fire hose nailed to a wall. For most of recorded ocean history, that hose has sprayed in roughly the same direction. Now the nails are loosening, the hose is creeping upward, and every few years it lurches a little more. Why does any of this matter to a person sitting in Texas, or Manila, or Berlin? Because the Gulf Stream is not just a current. It is the visible top layer of the largest heat redistribution system on Earth, the Atlantic Meridional Overturning Circulation, often shortened to AMOC. The Gulf Stream is the engine's exhaust pipe. When the engine stutters, the pipe is the first thing that moves. And here is what makes scientists pause. Computer models that simulate this entire system show one specific behavior right before the engine fails. The Gulf Stream drifts north, then, decades before the system fully breaks down, it jumps. Not a gentle slide, a sudden leap of more than 200 kilometers in just 2 years. The drift part has already been observed, the leap has not. Yet, forecasters at university labs across the United States, the Netherlands and Germany are now treating the Gulf Stream's position the way air traffic controllers treat a flight path. They check it, they cross-reference it, they look for any sign that the gradual creep is about to become something faster, sharper, and far harder to walk back. In 2025, a team at the University of Miami pulled 20 years of data from 4 deep ocean monitoring stations stretched across the western Atlantic. Every single station showed weakening flow. From the tropics up to the mid-Atlantic, the same signal, a consistent, basin-wide slowdown. Senior author Shane Ellipott called it the canary in a coal mine. What you are about to learn is how this current works, why it can fail, and what scientists fear is coming if it does. Because the next layer of this story is not on the surface. It is buried 2 miles deep where a hidden river is losing its strength. 2 miles below the surface of the North Atlantic, a river is flowing south. You cannot see it, you cannot hear it, but it carries more water than every river on Earth combined, multiplied many times over. This is the deep half of the Atlantic Meridional Overturning Circulation. The other half, the warm, salty surface flow heading north, is what most people call the Gulf Stream. Together, they form a vast loop that wraps around the entire Atlantic basin. Picture a conveyor belt at an airport. Bags travel one direction on top, then drop down and return underneath. Now stretch that belt across an ocean and turn it sideways. That is the AMOC. Warm water leaves the equator. It rides north along the surface, releasing heat into the air as it goes. By the time it reaches the seas around Greenland and the Norwegian coast, it has cooled. Cold water is heavier than warm water. It sinks. It plunges thousands of feet, joins the southbound deep current, and begins a slow journey back towards the southern hemisphere. There, it rises again, warms, and the cycle starts over. A single full loop takes around 1,000 years. The engine driving this loop is not wind, it is density. Two ingredients control how dense ocean water becomes: temperature, which everyone understands, and salinity, how much salt the water carries. Tropical evaporation pulls fresh water out of the surface, leaving the remaining water saltier. Salty water sinks more easily than fresh. As the warm, salty current travels north and cools, it becomes the densest water in the entire Atlantic. That is what triggers the plunge near Greenland. Take away the salt, or take away the cold, and the engine stalls. The AMOC moves an almost unbelievable volume of water. Oceanographers measure it in a unit called the sverdrup. One sverdrup equals 1 million cubic meters of water per second. The healthy AMOC runs at roughly 17 to 20 sverdrups. That is the equivalent of pumping the flow of every river on the planet, northward, then southward again, every single second of every single day. It is also the largest moving heat machine on Earth. The amount of warmth it carries is roughly equal to 1 million large nuclear power plants running at full output, all delivered to the high latitudes of the Northern Hemisphere. This is why Europe is not Canada. A city like Bordeaux, France, sits at almost the exact same latitude as Montreal. One has olive trees and vineyards, the other has frozen rivers and sub-zero winters. The difference is the heat pumped across the Atlantic by this current system. Without the AMOC, Bordeaux would freeze. For most of human civilization, the conveyor has been steady. The wheat fields of Britain, the rice paddies of West Africa, the monsoons of India, all of them rely on weather patterns that exist because this loop keeps turning at full speed. But the loop is slowing. Direct sensor measurements taken since 2004 suggest the AMOC has weakened by 10 to 20% in just 2 decades. Hundreds of millions of gallons of water per second that used to head north are no longer making the trip. The conveyor is dragging, and that drag is showing up first in the place where the warm water peels away from the American coast, the same place forecasters are now watching obsessively. To understand why one current can hold continents in balance, we need to look at exactly what Europe gets out of this deal, because the answer is bigger than mild winters. Stand on a winter beach in Lisbon, Portugal. The water is cold but swimmable. The air hovers above 50 degrees Fahrenheit. Now travel directly west across the Atlantic, holding the same latitude. You will land in New York City, where the Hudson River freezes and people shovel snow off their stoops. Same line on the globe. 2 completely different climates. That gap is the Atlantic meridional overturning circulation working in your favor. Europe sits roughly 9 degrees Fahrenheit warmer than it has any right to be, given how far north it is. London, Berlin, Stockholm, Amsterdam. These cities exist on the same latitudes as parts of Labrador and Hudson Bay in Canada, places where year-round settlement is sparse and ice locks the harbours solid for months. The reason Europeans can live, farm and trade across these northern lands is the warm water flowing past their shores. Here is how it works on a daily level. The Gulf Stream and its extension, the North Atlantic Drift, push roughly 15 petawatts of heat energy toward Europe each year. A petawatt is a quadrillion watts. The number is so large it loses meaning. So picture it this way. Every winter day, the ocean off the coast of Ireland releases enough warmth into the sky to heat every home in the United States, simultaneously, with surplus left over. That heat does not stay over the ocean. Westerly winds, The prevailing breezes that blow from west to east across the mid-latitudes pick up the warmth and carry it inland. By the time those winds reach Paris, Munich, or Warsaw, they have already donated their heat to half a continent. Without that delivery, winter Europe would look like winter Manitoba. A useful comparison sits inside Britain itself. The southern coast of England, near Cornwall, grows palm trees. They survive year-round because the ocean nearby never drops below about 10 degrees Celsius, even in February. Cornwall is at roughly the same latitude as Newfoundland in Canada, where icebergs sometimes drift past in summer. Two coastlines, same line on the map. One has palm trees, one has icebergs. The current is the difference. The benefit reaches further than temperature. Rainfall patterns in Western Europe are shaped by warm Atlantic moisture. The wheat belts of France, the dairy farms of Ireland, the olive groves of Spain, all of them depend on weather systems that form because warm water sits to the west, evaporating into the prevailing winds. This is why the slowdown that started showing up in the data is not a niche scientific curiosity. It touches the food supply of 500 million people. It touches energy demand across an entire continent. A meaningful drop in the heat being delivered by the AMOC could push average winter temperatures in northern Europe down by more than 5 degrees Celsius, enough to lock out crops, cripple gas reserves, and reshape every winter Europeans have known for centuries. The strange twist is that all of this hangs on a single physical condition. The water arriving near Greenland has to be salty enough to sink. If too much fresh water pours in, from melting ice, from changed rainfall, from anything at all, the sinking slows. The conveyor drags. The heat delivery weakens. That is, the lever climate is now pulling on. And the place where the lever is being pulled hardest is a stretch of ocean off North Carolina, where the warm current is slipping out of position. That spot has a name. Forecasters now repeat it like a code word. Cape Hatteras is a long, thin barrier island jutting out from the coast of North Carolina into the Atlantic. It is famous for shipwrecks. More than 2,000 vessels have gone down in the waters offshore, earning the area the nickname Graveyard of the Atlantic. Strong currents collide here. The continental shelf drops away sharply. The weather can turn vicious without warning. What very few people outside of climate science know is that Cape Hatteras is also the most important monitoring point in the entire Atlantic Ocean. The reason is geometry. The Gulf Stream flows north along the coast of Florida, Georgia, and the Carolinas, hugging the continental shelf the entire way. It is essentially trapped between the coastline and the open ocean. Then, right around Cape Hatteras, the shelf sharply turns east. The current loses its wall. It separates from the coast and shoots out into open water, becoming the free-flowing jet that carries heat across the Atlantic. That separation point is called the crossover. Oceanographers track it at a specific longitude, 71.5 degrees west. For most of the satellite era, the Gulf Stream peeled off the coast at a fairly stable latitude. Year to year it wobbled a bit. Decade to decade it stayed put. That stability ended. Researchers at Utrecht University in the Netherlands, led by climate physicist René van Westen, ran an experiment that became one of the most discussed papers of 2026. They built a high-resolution computer simulation of the Atlantic and ran it forward in time, slowly adding fresh water to the North Atlantic to mimic Greenland melting. They watched what happened to the AMOC. The current weakened. Then it collapsed. But before the collapse, the simulation did something the team had not expected. The Gulf Stream's separation point at the crossover started drifting north. First slowly, then, with no warning, it leaped. In the model, it jumped 136 miles north in just 2 years. That leap occurred about 25 years before the AMOC actually shut down. In other words, the simulation produced a tripwire, a specific measurable signal that fires before the rest of the system fails. So the team did the obvious thing. They went looking for that signal in the real world, They pulled 3 decades of satellite altimetry data, measurements of sea surface height that reveal exactly where currents are flowing. They added subsurface temperature records going back to 1965. Both datasets pointed the same direction. The Gulf Stream's crossover at Cape Hatteras has been drifting north for the entire satellite era. With statistical confidence, the trend is real. That is the gradual stage of the model's 2-stage warning, the slow drift. Whether the second stage, the abrupt leap, has begun or is about to begin is what forecasters cannot yet say. Some signals point that way. Sea surface temperatures off North Carolina are warming faster than the surrounding ocean. Coastal flooding patterns from Florida to the Outer Banks are shifting in ways that match what a poorly anchored Gulf Stream would produce. Researchers at multiple institutions have started checking the crossover position weekly, not annually. Weekly. A small island chain in North Carolina has become the closest thing the climate system has to a check engine light. And inside that engine, 2 separate stages of warning are flashing, one steady, one yet to come. Understanding those 2 stages is where the real story gets unsettling. Most natural systems break in one of 2 ways. Some fail gradually, a glacier retreats inch by inch over a century, a forest thins out tree by tree. Other systems fail suddenly. A dam holds, then it does not. A fault line is silent, then it is not. The Atlantic meridional overturning circulation seems to combine both behaviors. And that is what makes it so dangerous to forecast. The 2026 Utrecht simulation revealed the dual nature in detail. When researchers traced the Gulf Stream's response to a slowly weakening AMOC, they did not see one continuous slide. They saw 2 distinct phases. Phase 1 was the slow walk. Over hundreds of simulated years, as the AMOC gradually lost strength, the Gulf Stream's separation latitude at Cape Hatteras drifted north by about 133 kilometers, roughly 83 miles. A foot at a time, patient, almost invisible. Phase 2 was the lurch. After centuries of creeping north, the current suddenly snapped. In just 2 simulated years, it jumped another 219 kilometers, about 136 miles, northward. This was not a continuation of the drift. This was a regime change. The atmosphere and ocean physics around the crossover reorganized themselves into a new configuration. That sudden phase appeared roughly 25 simulated years before the AMOC's main body collapsed. Think of it like a person tripping. They stagger forward for several steps, off balance, fighting gravity. To an observer, it looks like recoverable wobbling. Then, in a single moment, the foot misses, the body tips past the angle of return, and the fall happens. The wobbling and the fall belong to the same event. They just look completely different from the outside. The team's lead scientist, René van Westen, summarized it bluntly. There is the gradual drift, related to general weakening, and then there is the jump, which signals the system is approaching a point where recovery becomes physically impossible. Why does this happen? The answer comes down to the deep current sitting underneath the Gulf Stream. A second flow, called the Deep Western Boundary Current, runs in the opposite direction along the same continental slope. It is the cold return leg of the conveyor belt. Water that already sank near Greenland is now heading south at depth. The interaction between these 2 currents, one warm on top, one cold below, helps lock the Gulf Stream against the coast. The deep current effectively pins the warm one in place through subtle pressure dynamics. When the deep western boundary current weakens, that pin loosens. The Gulf Stream gradually slides north. As long as the deep current keeps weakening slowly, the slide stays gradual. But once the deep flow drops past a certain threshold, the entire pinning mechanism collapses. With nothing holding it down, the warm current snaps north into a new equilibrium. That is the lurch. Multiple independent studies have now confirmed the deep western boundary current is, in fact, weakening. The University of Miami's 2025 analysis of 4 monitoring sites found consistent decline. The Utrecht satellite analysis found the matching surface drift. Both halves of the early warning system are showing exactly what the model predicted would happen during Phase 1. Phase 2 has not been observed yet, but the conditions that produce it appear to already be lining up. This is why forecasters use the word edge, not in a poetic sense, in a literal one. The Atlantic appears to be sitting at the edge of one phase, about to tip into the next, and the silent giant beneath the surface, the deep current losing its grip, is the next part of this story. 2,000 meters below the swirling blue of the Gulf Stream, in pitch-black water no human will ever see firsthand, another current is flowing. It moves in the opposite direction. It carries water as cold as a refrigerator, and it is one of the most influential rivers on the planet, even though almost nobody outside of oceanography has heard its name. This is the deep western boundary current, the unsung partner of the Gulf Stream, the return leg of the global conveyor. To picture it, imagine a layered cake of ocean water off the coast of North Carolina. The top layer is the warm, fast Gulf Stream heading north. Beneath it, separated by an invisible boundary, sits a much larger body of cold, dense water heading south. The southbound layer is far slower than the surface current, but it is enormous. It hugs the same continental slope, only mirrored upside down. This deep current is the water that already finished its long journey. Tropical surface water that traveled north, gave up its heat to Europe, sank near Greenland, and is now creeping back to the equator at depth. It carries the AMOX exhaust. The fact that it is colder, denser, and saltier than the warm water above is what keeps the entire conveyor turning. In a healthy Atlantic, the volume of water moving south through this deep current roughly matches the volume of warm water moving north on the surface. Balance is the system's natural state. That balance is breaking. In 2025, a team led by physical oceanographer Shane Elipott at the University of Miami pulled together 2 decades of measurements from 4 ocean monitoring arrays installed along the western boundary of the North Atlantic. These arrays use seafloor-anchored sensors that continuously log pressure, temperature, density, and current speed. By comparing changes in bottom pressure across years, the team could estimate how much deep water was actually flowing past each station. The results were unambiguous. Every single one of the 4 sites showed a decline. The weakening stretched from the tropics near 16 degrees north all the way up past 42 degrees north. Not a localized blip, a basin-wide signal. Elipott called the western boundary the canary in a coal mine for the entire AMOC. The phrase has stuck. Every time researchers reference the location, they mean something specific. The deep current along this edge is the most sensitive part of the system to overall weakening. When it slows, the whole conveyor is slowing. Why does this slowdown matter for the surface drama at Cape Hatteras? Because of pinning. Oceanographers have known for years that the position where the Gulf Stream peels off the coast is partly controlled by what is happening underneath. The deep western boundary current produces a subtle steering effect on the warm current above through interactions involving rotation, vorticity, and pressure gradients. Strong deep flow keeps the surface current locked in. Weak deep flow lets it wander. That is exactly what the satellite data shows. As the deep current has weakened over the past 2 decades, the Gulf Stream above has begun drifting north. The 2 trends are not coincidence, they are linked physics. And the deep current is not weakening for mysterious reasons. It is weakening because the water that feeds it, the cold, dense, sinking water near Greenland, is becoming less dense, less cold, and less ready to sink. Something is interfering with the plunge that powers the entire system. That something is fresh water. Massive amounts of it, pouring off an island larger than Mexico, melting at speeds that have shocked even the scientists who study it. Greenland is shrinking. Not gradually, not gracefully. Roughly 280 billion tons of ice are melting off the island every single year. That meltwater is fresh, and the entire Amazon gen runs on the opposite of fresh. To understand why a melting island can disrupt a global ocean conveyor, you have to understand what salty water actually does. Salt makes water heavier. The more salt, the denser the water, and the more readily it sinks when cooled. The North Atlantic sinking zone near Greenland and the Norwegian Sea works because the warm water arriving from the south is unusually salty after baking under tropical sun. By the time it reaches the cold north, it cools, becomes the densest water in the Atlantic, and plunges thousands of feet down. Now imagine pouring a giant glass of fresh water into the exact spot where the sinking happens. The fresh water dilutes the salt. The diluted water is lighter. Lighter water does not sink as easily. The plunge slows, and right next to the plunge zone sits Greenland, an ice cap up to 2 miles thick, holding enough frozen fresh water to raise global sea levels by 23 feet, if it all melted. As the planet warms, that cap is shedding water at an accelerating pace. Glaciers carve icebergs into the sea. Surface meltwater rivers run blue and ferocious across the ice in summer. Bottom melting, where warm ocean water erodes glaciers from underneath, has sped up dramatically. Every drop of that fresh water flows into the sinking zone. Climate scientists call this process freshwater forcing. When they want to test how vulnerable the AMOC is, they run computer simulations that pour fresh water into the North Atlantic and watch what happens. The results are consistent across many studies. Add enough fresh water, and the conveyor slows. Add even more, and it stops. The amount of fresh water it actually takes is alarmingly small relative to the size of the ocean. Researchers measure freshwater forcing in sverdrups, the same unit used for the AMOC's main flow. A freshwater input of just 0.3 sverdrups, about 300,000 cubic meters per second, was enough to push half of the climate models tested in 2023 hosing experiments into a near-collapse state. For comparison, current Greenland melting hovers around 0.01 sverdrops. That sounds reassuring until you realize the rate has tripled since the 1990s and continues to climb. Antarctic melting adds even more freshwater indirectly through global redistribution. Arctic sea ice loss compounds the effect. There is a more troubling point. Most major climate models do not yet include realistic Greenland melt. The IPCC's standard projections assume freshwater input from melting ice is essentially zero. That is why a number of prominent oceanographers, including Stefan Rahmstorf at the Potsdam Institute, have argued the official projections systematically underestimate how fast the AMOC will weaken. Rahmstorf's view is blunt. The pessimistic models, the ones showing the strongest weakening, appear to be the realistic ones. The official consensus may be lagging behind the physics. A 2026 study used a corrected version of the models that better accounts for salinity and freshwater. The result was a projected 51% slowdown of the AMOC by the end of this century. That is 60% stronger than the standard model average. The IPCC itself classifies a 50% slowdown as substantial weakening, a polite scientific phrase for what would be one of the largest climate system shifts in human history. The salt is losing, the fresh water is winning, and the consequences ride on a single battle being fought in a region most people will never visit. If you could shrink yourself down and ride a single water molecule from the equator to Greenland, you would witness one of the strangest tug-of-wars on Earth. It is a quiet battle fought across thousands of miles, with no winners and no losers, only a balance that holds the climate of half the planet in place. The contest is between salt and fresh water, and right now fresh water is gaining ground. Salt does something almost magical to water. A teaspoon of salt dissolved in a glass of water makes it ever so slightly heavier. Multiply that by a planet's worth of ocean, and the difference becomes enormous. Salty water sinks, fresh water floats, That single fact, the difference in density between salty and fresh, drives every major deep ocean current on Earth. In the Atlantic, the warm surface flow heading north begins its journey already saltier than average. The reason is the tropics. Hot equatorial sun evaporates massive amounts of water off the ocean surface. The water that escapes into the air is pure. The salt stays behind, so the surface water steadily concentrates, becoming saltier as it moves through the tropical Atlantic. That salty water keeps moving north. It crosses through the Caribbean, slides up past Florida, and eventually reaches the latitudes near Iceland and Greenland. By the time it arrives, it has cooled significantly. Cold and salty is the heaviest combination ocean water can have. It sinks like a stone. This sinking is not a side effect of the AMOC. It is the AMOC. Without it, the entire conveyor stops. And here is the cruel feedback that scientists worry about. The system has a self-stabilizing mechanism, but it also has a self-destructing one. When salty water arrives, sinks, and pulls more salty water in behind it, the loop reinforces itself. Strong AMOC delivers more salt north, which makes more sinking, which strengthens the AMOC. A virtuous cycle. But the same physics works in reverse. When fresh water dilutes the sinking zone, less salty water sinks. That weakens the pull on incoming saltiness. So less salt reaches the north, which makes the next round of sinking even weaker. A vicious cycle. This is what oceanographers mean when they say the AMOC has bistability, a fancy word meaning the system has two stable states it can sit in. One is the strong, salty, fast-flowing conveyor we currently know. The other is a weak, fresh, sluggish version that only delivers a fraction of the heat northward. Once the system slips out of one stable state, the feedbacks can drag it into the other and lock it there. Researchers studying ancient ice cores from Greenland have found evidence the Atlantic has switched between these two states many times in the deep past. Each switch happened over decades, not centuries. Each one rewrote the climate of the Northern Hemisphere. The 2026 review paper covered earlier explicitly concluded the present-day AMOC is sitting in a bistable regime. Not metaphorically, mathematically. The system can flip. A 2024 study published in Science Advances introduced a new physics-based early warning indicator tied to freshwater transport at the southern edge of the Atlantic. The team's conclusion was clipped and chilling. The AMOC, they wrote, is en route to tipping. Other scientists pushed back. Some argued the wind-driven upwelling in the Southern Ocean, far from the North Atlantic, will keep the conveyor partially alive even under extreme conditions. The debate is real and ongoing, but every side agrees the salt versus fresh battle is the central drama. Whichever side is winning at any given decade decides whether the conveyor speeds, slows, or stops. Right now, the salt is losing ground, and the most stunning evidence yet of how fast the loss is happening came from a 2026 study that left even hardened oceanographers shaken. In late February 2026, a paper landed in Communications, Earth and Environment that most working oceanographers would later describe with the same words. They had not expected the numbers to look like that. The lead author was René van Westen, a postdoctoral researcher at Utrecht University, who had already become one of the more cited names in AMOC science. Working with senior climate physicist Henk Dijkstra, Van Westen had built a high-resolution ocean simulation. The grid spacing was tight, 1/10 of a degree of latitude and longitude, which is the kind of resolution that captures fine-scale features like the Gulf Stream's separation point in real detail. Most climate models smear those features into rough averages. This one did not. The team applied a slowly increasing freshwater input to the North Atlantic in the simulation, mimicking an accelerating melt of Greenland and surrounding ice. They ran it for hundreds of simulated years. Then they tracked what happened to the Gulf Stream at a specific longitude, 71.5 degrees west, the crossover point at Cape Hatteras. The early results were predictable. As the AMOC weakened, the Gulf Stream's separation latitude crept north, slowly. Over 392 simulated years, the crossover migrated about 83 miles, roughly 13 kilometers per simulated decade. Then the model did something unexpected. In a window of just 2 simulated years, the crossover snapped 219 kilometers north, 136 miles. In 2 years. For context, that kind of shift in the real ocean would mean the Gulf Stream peeling off the coast, not at Cape Hatteras, but somewhere up near the latitude of New York City. Fishermen who track the warm water for tuna and marlin would suddenly find themselves working in a new world. Sea surface temperatures along the entire mid-Atlantic coastline would reorganize within months. That sudden snap occurred about 25 simulated years before the AMOC itself fully collapsed. That timing is the part that made the paper an instant talking point in climate science. Van Westen and Dijkstra had not just shown the Gulf Stream responds to AMOC weakening, they had shown the response has a specific abrupt and detectable warning stage that fires decades before the main system fails. In other words, they had identified a possible tripwire, a measurable signal in real-world satellite data that could tell us when the AMOC has crossed a point of no return, 25 years before the curtain actually drops. The question every reader of the paper immediately asked was the obvious one: is the Gulf Stream already shifting in real life? The team had anticipated that. The same paper included an analysis of 3 decades of satellite altimetry from 1993 to 2024, plus subsurface temperature records going back to 1965. Both data sets showed a statistically significant northward trend in the Gulf Stream's crossover position, the exact pattern the model predicted for Phase 1, the slow drift. What is unknown is whether the abrupt phase has begun. Some researchers, like Maya Benyami, a tipping point researcher, urged caution. The result, she said, points to Gulf Stream changes as a possible warning signal, but more work is needed to confirm that across different models. Models can disagree. Phase 2 might happen later than the simulation suggests. It might happen sooner. Real-world bathymetry, the underwater shape of the seafloor, and the actual rate of Greenland melt could shift the timing. Others like Stefan Rahmstorff took a different view. He has called the broader pattern of recent results, unfortunately, the realistic scenario. The pessimistic models keep being confirmed by observations. The optimistic ones keep falling away. Whatever the timing, the 2026 paper changed the conversation. The Gulf Stream is no longer just a current. It is a dial, a measurable, visible, satellite trackable indicator that tells us exactly where the AMOC is in its life cycle. And the dial is turning the wrong way. Behind that dial sit 20 straight years of sensor data telling a darker story. In April of 2004, a small team of oceanographers and engineers lowered a series of instruments into the Atlantic Ocean along an invisible line stretching from the Bahamas to the Canary Islands. The line sits at 26.5 degrees north latitude. The instruments were built to do one job: measure the AMOC continuously, 24 hours a day, year after year. The system they installed is called the Rapid Array. It has been running ever since. As of 2026, it is the longest operating direct measurement of the Atlantic conveyor in existence. Other arrays have joined it over the years. In the tropics, in the subpolar gyre off the coasts of North and South America. Together, they form the closest thing humanity has to a heart monitor for the world's most important current system. For the first decade of Rapid's life, the data showed something approaching the expected pattern. The AMOC strength fluctuated naturally year to year and season to season. Some years it ran a little faster, some years it ran a little slower. The average held roughly steady. Around the mid-2000s, that started to change. By 2010, Rapid was registering a measurable decline in AMOC strength. Some scientists initially questioned whether it was just decade-scale natural variability. The Atlantic does have multi-year cycles, after all, but by 2015 the trend was unmistakable. By 2020, debates over whether the slowdown was real had largely ended. The remaining debate was about how fast and how much. The 2025 study from the University of Miami pushed the picture further. The team did not just rely on rapid, they pulled data from 4 separate monitoring arrays spread across roughly 26 degrees of latitude, from the tropics near 16 degrees north all the way up to 42 degrees north, off the coast of the northeastern United States. Every site told the same story: decline, consistent, sustained, measurable weakening of the deep flow along the western boundary. The numbers, when stripped of jargon, are unsettling. Direct observations now suggest the AMOC has dropped in strength by roughly 10 to 20% since the mid-2000s. Translating that into volume, hundreds of millions of gallons of water per second that used to flow north along the surface are no longer making the trip. The amount of heat being delivered to the North Atlantic has fallen accordingly. And the trend is not flattening out. Each new year of data has reinforced the slope. Shane Elapod, the lead author of the Miami study, put it in plain terms. The same models predicting the AMOC is heading toward a tipping point are now being validated by real-world data showing the predicted weakening is actually occurring. That is the part that shifts the conversation from hypothetical to operational. The physics behind the projections is matching the observations. There is one important caveat scientists keep emphasizing. 2 decades of data is enough to establish a trend with statistical confidence, but not enough to fully separate human-caused weakening from natural multi-decadal variability. The Atlantic has slow cycles that play out over 40, 50, even 60 years. Some skeptics argue the decline since 2004 could be partly that. The team at Miami estimated humanity will need until around 2033, 29 years of continuous measurement, before the human signature can be confidently extracted from the noise. Until then, the signal sits in a strange zone, almost certainly real, almost certainly bad, not yet attributable with full statistical certainty to global warming. But the 2033 deadline is not really comforting. By the time the data definitively confirms the cause, another decade of weakening will have occurred. Every year of waiting is a year of further drift. The canary may not be singing anymore. The question is whether anyone will act before it goes silent altogether. Because while the sensors quietly tally their decline, the climate models that simulate the future are reaching conclusions much darker than the official numbers suggest. For most of the past 2 decades, the official climate forecast for the AMOC has been cautious. The Intergovernmental Panel on Climate Change, the global body that synthesizes climate research for governments, has consistently said the AMOC will very likely weaken through the 21st century, but that an outright collapse before 2100 is not expected, with medium confidence. That careful language has shaped policy. It has shaped how seriously coastal cities, farmers and finance ministers have treated the risk. And in 2026, a single study suggested that careful language has been wrong. The paper was published in Science Advances in April 2026 by a team led by Valentin Portman at the INRIA Research Centre in Bordeaux, France. Portman and his collaborators went looking for systematic errors in how climate models simulate the Atlantic. They focused on 2 specific biases that had been quietly bothering oceanographers for years. The first bias was in salinity. Standard climate models simulate the South Atlantic as not salty enough. They underestimate how much salt is actually concentrated in the water that flows up from the southern hemisphere into the AMOC's warm leg. Less simulated salt means lighter simulated water, means less simulated sinking up north. The second bias was in temperature. The same models simulate the North Atlantic as too cold. Cold water already wants to sink, even if it is not particularly salty. So an artificially cold North Atlantic can compensate for the artificially weak salinity and produce a simulated AMOC that looks healthier than it actually is. The 2 biases together had been letting models off the hook. They were cancelling each other out and producing AMOC projections that looked artificially stable. Portman's team applied a statistical technique called ridge-regularized linear regression, a method common in machine learning but rare in climate science. To correct the biases simultaneously, they fed the corrected models multiple variables at once: past AMOC strength, salinity patterns, temperature distributions. They trained the models to match real-world observations more tightly, then ran the projections forward. The result was striking. The corrected models projected the AMOC would weaken by approximately 51% from its pre-industrial average by the year 2100. That is roughly 60% stronger than the average projection from standard, uncorrected climate models. Even worse, the uncertainty bars around the corrected projection were significantly tighter than before. The team had not just found a more pessimistic answer, they had found a more confident one. The IPCC's own classification calls a 50% slowdown substantial weakening. Substantial weakening would be the largest shift the Atlantic has experienced in modern human history. David Thornalley, a professor of ocean and climate science at University College London, said the projected weakening being larger than previously thought is clearly worrying. Other commentators were sharper. Stefan Ramstorff at Potsdam noted that the pessimistic class of climate models, the ones predicting strong AMOC decline, appear, based on this and other recent work, to be the realistic ones. The optimistic projections that informed earlier IPCC reports may simply have been wrong. Portman himself was direct about why this matters. The AMOC is enormously complex, he explained, and depends on multiple interacting processes. Trying to project its future from a single variable, like past current strength, misses critical information. Adding more variables, salinity, temperature, freshwater transport, produces a much more reliable picture. When you do that properly, the picture darkens. There is a second concerning detail. Even the corrected models do not include realistic Greenland meltwater. None of them do. Yet, adding accurate freshwater forcing would likely make the projected weakening even larger. Some researchers have argued the true 21st century slowdown could exceed 60 or even 70%, simply because the meltwater contribution has been ignored across the board. The implications stretch from European agriculture to the path of Atlantic hurricanes, and one of the most concrete consequences is already showing up along the east coast of the United States, in flooding patterns nobody could explain. Residents of Norfolk, Virginia have a phrase for it. They call it sunny day flooding. On clear days, with no rain, no storm offshore, no obvious reason at all, the streets in the lower neighborhoods fill with seawater. It rises up through the storm drains. It pools at intersections. Cars stall. Foundations sit in salt water for hours before the tide retreats and the streets dry out. The phenomenon is not unique to Norfolk. Charleston, Miami Beach, Annapolis, Atlantic City, every major city along the east coast of the United States has been logging more of these flooding events every decade. By the early 2020s, some neighborhoods were experiencing dozens per year. By 2025, the trend lines on official tide gauge charts were nearly vertical. For a long time, the explanation focused on global sea level rise. Warming oceans expand. Melting ice adds water to the global system. Sea levels rise. Coastal cities flood more often. That story is true, and it accounts for most of the long-term increase. But it does not account for everything. East Coast flooding has been accelerating faster than the global average. Some analyses showed sea levels along the northeastern United States rising at roughly twice the global rate. That extra ingredient was not explained by simple thermal expansion or ice melt alone. Something specific to the Atlantic was making things worse. In 2025, a study by federal climate researchers in the United States quietly added a new piece to the puzzle. They found that the AMOC's recent weak phase had directly contributed to as much as 50% of flooding events along the northeastern coast of the United States since 2005. Half half of the flooding nobody had previously been able to explain. The mechanism is not subtle once you understand it. The Gulf Stream, when running at full strength, actually pulls water away from the east coast. Its strong flow creates a kind of pressure gradient that holds sea levels along the coast slightly lower than they would otherwise be. When the Gulf Stream weakens, and it has been weakening, that suction effect slackens. Water that used to be pulled away from the coast now piles up against it. Add a high tide, a full moon, a brisk onshore wind, and suddenly the streets of Norfolk fill with salt water on a day with no clouds. The combination is brutal for coastal infrastructure. Roads designed to handle occasional storm surges are now corroding under chronic immersion. Storm drains that worked perfectly in 1990 now carry tidewater inland on a regular basis. Sewer systems are increasingly contaminated by intrusions of salt. Low-lying real estate values are starting to reflect the new reality. Insurance companies have begun pulling out of certain coastal zip codes entirely, and the projected 51% AMOC slowdown by 2100 would dramatically extend this dynamic. If the conveyor weakens further, and the satellite sensor and climate model evidence all point toward continued weakening, the East Coast can expect an additional layer of sea level rise on top of whatever global oceans are doing. Some projections suggest the additional regional rise could reach a foot or more by 2100 from AMOC weakening alone. A foot does not sound like much when you say it. Stand at the high tide line on a Norfolk street, mark a foot above the pavement, and try to imagine that line as the new daily high. Most of the lower city would simply not function. This is the AMOC story made concrete. Not abstract climate science, not far-off Greenland melt, wet basements in Maryland, stalled commutes in Charleston, dying lawns in Florida from saltwater intrusion. The conveyor is slowing, and one entire shoreline is paying the bill in real time. The slowdown ahead will not be linear. The next 50 years could push these effects from chronic to catastrophic. Numbers in climate science have a way of going numb after a while. Half a degree warmer, 20 centimeters of sea level rise. Each statistic, on its own, sounds either dull or arguably manageable. The 2026 Portman study's central finding, a projected 51% slowdown of the AMOC by 2100, fits the same pattern at first glance. Half a current. Bigger than expected, sure, but how does a person actually picture half a current? The honest answer is that the picture is much worse than the number suggests, because the impacts of a slowdown do not scale linearly with the percentage. They cascade. Start with heat delivery. The AMOC currently transports around 15 petawatts of heat northward. A 51% reduction would mean roughly 7.5 petawatts of heat that no longer arrives at the high latitudes of the North Atlantic. That heat does not vanish. It stays trapped in the southern hemisphere and the tropics, intensifying warming there while leaving northern Europe and the northeastern United States colder than they otherwise would be. For Britain, France, Germany, the Low Countries, and Scandinavia, the consequence is a pulling of two opposite climate forces. Global warming pushes temperatures up, AMOC weakening pulls them down. In the high emission scenarios, warming wins overall, and Europe still gets hotter, just less hot than the rest of the planet. But in mid-emission scenarios, the slowdown can partially or fully cancel the warming, and northern Europe ends up cooler than it is today. Average winter temperatures in some northern European cities could drop by several degrees Celsius, modest sounding in print, brutal in practice. Heating systems sized for current winters would be inadequate. Crop varieties bred for current growing seasons would fail. Wildlife adapted to particular ranges would shift, die, or both. Sea level rise comes next. As the AMOC slows, sea levels along the northeastern United States rise faster than the global average. A 51% slowdown could add an extra foot or more of rise on top of whatever the global ocean is doing. For cities like New York, Boston, Norfolk, and Miami, That extra foot would push routine king tides into what is currently considered a 100-year flood. Subway systems, tunnels, airports and ports would face sustained repetitive inundation rather than occasional disasters. Storm patterns would reorganize, with a weaker AMOC redistributing heat differently. Atmospheric circulation patterns over the Atlantic would shift. Some evidence suggests Atlantic hurricanes could become more frequent, more intense, or both, though this is one of the more uncertain corners of the science. European winter storms, by contrast, would almost certainly intensify, drawing extra energy from the temperature contrast between a colder northwest and a still warm tropical Atlantic. The tropical rain belt, the band of intense rainfall that wraps around the equator and feeds monsoons across West Africa, India, and Southeast Asia, would migrate southward in response to the weakened heat transport. Hundreds of millions of people in regions that depend on monsoon agriculture would face unpredictable, often reduced rainfall. West African farms growing sorghum, millet, and maize would see year-to-year yields collapse. South Asian rice harvests could falter. Even ecosystems would respond. The plankton populations that anchor the North Atlantic food web could be cut by more than half, according to some projections, as deep nutrient mixing slows and ocean stratification increases. Fisheries from Iceland to New England would feel the loss within a generation. Maria Paz Chidochimo, an oceanographer who has worked extensively on the AMOC, summarized the situation bluntly. "There is enough scientific evidence," she said, "of AMOC variability, slowdown, and current environmental impacts." The phrase she used to follow that statement was simple: nations need to prepare now. And yet the deepest concern about the AMOC is not the slowdown by itself, it is the possibility that the slowdown crosses a threshold and tips the entire system into a fundamentally different state. To understand that risk, you have to understand a strange property of the conveyor that sets it apart from most other components of the climate system. Most things in nature change gradually. A river deepens, a coastline erodes, a glacier retreats. The relationship between cause and effect is roughly proportional. Twice as much pressure produces roughly twice as much response. The AMOC does not work that way. It belongs to a small and dangerous category of systems known as bistable. And bistability is the reason climate scientists lose sleep over it. A bistable system has two stable states. Each state is self-reinforcing. The system can sit comfortably in one state for a long time, even when conditions change, because internal feedbacks keep dragging it back to equilibrium. But push the system far enough, past a specific threshold, and it suddenly flips to the other stable state. Once flipped, the same feedbacks that kept it in the first state now keep it locked in the second. Reversing the flip is not a matter of unwinding the original push. The system has new physics. A simple way to picture bistability is a marble in a double cup tray. Two depressions, side by side, separated by a small ridge. The marble can rest in either cup. If you tilt the tray gently, the marble wobbles but stays put. If you tilt further, the marble leaps the ridge and rolls into the other cup. Now you must tilt the tray the opposite direction even harder to roll it back, because the ridge that previously protected one cup now protects the other. The AMOC has exactly this geometry. State 1, the present-day state, is a strong, salty, fast-flowing conveyor delivering heat north and powering deep-water sinking near Greenland. State 2, the collapsed state, is a weak, fresh, sluggish pattern with little to no deep-water formation and dramatically reduced heat transport. Both states are physically stable. The system can sit in either one for centuries. What forces the flip? Freshwater, heat, salinity changes, push the salty cold sinking pattern hard enough with fresh meltwater, and the conveyor weakens. Past a threshold, the weakening triggers a feedback in which less salty water reaches the north, so even less sinking happens. So even less salty water gets pulled in. The marble jumps the ridge. The conveyor lands in state 2. Climate scientists call this jump an AMOC tipping point. The exact threshold is unknown. It may be a specific level of cumulative freshwater forcing. It may be a specific temperature change in the North Atlantic. It may be a combination. What is known is that once the threshold is crossed, the new state is extraordinarily difficult to escape. Models that simulate AMOC collapse and then try to reverse it generally fail. The system stays collapsed for centuries, sometimes millennia. A 2026 review study in Reviews of Geophysics looked at the case for AMOC bistability across decades of research. The authors concluded that the evidence base in favor of bistability has broadened significantly in recent years. They also concluded that the present-day AMOC currently sits in a bistable regime. Not could sit, sits. A 2024 paper in Science Advances introduced a new physics-based metric for tracking how close the AMOC is to its tipping point, a measurement based on freshwater transport at the southern boundary of the Atlantic. The team's conclusion, stated directly in the paper, was that the AMOC is en route to tipping. Other groups have pushed back. A 2025 Nature paper argued that wind-driven upwelling in the Southern Ocean would prevent total collapse even under extreme forcing, because the deep water has to come up somewhere, and the Southern Ocean winds keep driving that upwelling regardless of what is happening up north. The implication is that the AMOC might weaken severely but not fully shut off. Other researchers find that argument plausible, but argue it does not prevent severe consequences from a major weakening. The debate is unresolved. What is not in dispute is the unusual nature of the system itself. The AMOC is not a slowly bending reed. It is a marble sitting on a tilted tray with one ridge between it and a very different climate world. There are reasons to believe that ridge has been crossed before, written into the deepest archives of Greenland's ice. In the 1980s, two scientists, a Dane named Willy Dansgaard and a Swiss researcher named Hans Oeschger, were studying ice cores drilled from deep within the Greenland ice sheet. The cores were like time capsules, with layers of ice stretching back tens of thousands of years. By analyzing the ratio of oxygen isotopes trapped in each layer, the two could reconstruct the temperature of Greenland during each year of the past. What they found stunned them. Greenland's temperature record over the last ice age was not a smooth, slow curve. It was a series of violent jumps, 25 times during the period from about 126,000 years ago to 11,700 years ago. Greenland's temperature spiked upward by between 15 and 27 degrees Fahrenheit. Each jump happened in just a few decades, geologically an instant. Then, after several centuries, the temperature would slide back down to Ice Age levels. Then, sometime later, another spike. The spikes were named after their discoverers, Dansgaard-Oeschger events, DO events for short, 25 of them in the last glacial period alone. For years, scientists puzzled over what could cause such enormous temperature shifts so quickly. Earth's orbit changes too slowly, volcanic activity is too small. The cause had to be something that could rearrange the entire climate of the North Atlantic in a matter of decades. There was really only one candidate: the AMOC. Subsequent research has built a strong case that DO events were driven by sudden flips of the Atlantic conveyor between weak and strong states. During the cold periods, the AMOC was weak. The marble was in one cup. Ice covered Greenland heavily. Heat transport northward was reduced. Then, for reasons still being unraveled, the conveyor would suddenly switch on at full strength. The marble jumped to the other cup. Tropical heat poured into the North Atlantic. Greenland warmed by 20+ degrees in a generation. Sea ice retreated. Storm tracks shifted. Climates from Europe to Asia reorganized. A few centuries later, the conveyor would weaken again, and the climate would slide back into the cold phase. The implication of DO events for our current situation is sobering. The AMOC has flipped repeatedly in the geological past. The flips happened on human timescales, fast enough that an entire civilization could be born and die in the warm phase between two cold ones. The flips were often triggered by changes in freshwater input to the North Atlantic, exactly the kind of forcing that Greenland is delivering right now. The Bistability discussed in the previous chapter is not a theoretical concern from climate models. It is a fact written into the Greenland ice itself. In 25 separate handwritten warnings, there is one important difference between the past flips and what could happen today. The DO events occurred during ice ages, when the planet was substantially colder than it is now. The freshwater forcing came from massive ice sheet collapses called Heinrich events, in which gigantic surges of icebergs broke off and flooded the North Atlantic. Today's planet is warmer, the polar ice less extensive, and the freshwater forcing comes from a different source: Greenland's surface and bottom melting accelerated by global warming. Whether the modern AMOC would respond to this kind of forcing in the same way the ancient AMOC did is the question that haunts the field. Some researchers think the warmer baseline makes a flip less likely because the marble starts in a deeper cup. Others argue the warming creates new pathways to instability that did not exist during ice ages. The matter is unsettled. What is not unsettled is the empirical reality of the past. The Atlantic conveyor has flipped before. It has flipped many times. Each flip rewrote the climate of the Northern Hemisphere within a single human lifetime. And if the modern conveyor does flip, even partially, the effects would be visible in cities people live in today, starting with one of the most famous on Earth. In June of 2025, two researchers at Utrecht University, René van Westen, the same scientist who later co-authored the 2026 Gulf Stream paper, and Michiel Baartsen, published a study that turned heads across European meteorological agencies. They used a high-resolution climate model called the Community Earth System Model to simulate what would happen to specific European cities under a scenario in which the AMOC collapsed and global average warming reached 2 degrees Celsius above pre-industrial levels. They picked cities people could relate to: London, Oslo, Amsterdam. Built in the Netherlands, they ran the simulations and tabulated the results city by city. Then they made their data public on an interactive online map so that policymakers and the public could see exactly what an AMOC collapsed future might look like for the places they live. The results for London were unsettling. Average winter temperatures in the city, currently sitting around 5 to 6 degrees Celsius, the number of days each year with sub-freezing temperatures, currently averaging around 2 or 3, would jump to 17.6. A 1 in 10 year cold extreme event, meaning the kind of cold snap a Londoner would expect to live through once a decade, would reach minus 19.3 degrees Celsius. That is roughly minus 3 degrees Fahrenheit, a temperature London has not seen in any modern record. For context, London's coldest winter on direct record is the winter of 1962 to 1963, when the Thames partially froze over and snow lay on the ground for months. Even that historic winter did not produce sustained temperatures near the model's projected 1 in 10 year extremes for an AMOC collapsed world. The Utrecht team's projections for Oslo were even more dramatic. Norway's capital sits at 59.9 degrees north. Today it has cold winters but a relatively temperate climate, by Nordic standards, kept above the worst extremes by the warm Atlantic. In an AMOC collapsed 2-degree warmer world, Oslo would experience below freezing temperatures for nearly half the year. 1 in 10 year cold extremes would reach approximately minus 48 degrees Celsius, minus 55 Fahrenheit. That is closer to interior Siberia than modern Scandinavia. Tim Lentham, the Climate Change and Earth System Science Chair at the University of Exeter, captured the situation in plain English. The extreme winters, he said, would be like living in an ice age. At the same time, the model showed summer temperatures barely changed compared to current conditions, slightly cooler than they would otherwise be due to global warming, but still hotter than pre-industrial summers. The result is a radical increase in seasonality, brutally cold winters, hot summers, a climate of extremes pulled apart at both ends. The mechanism is straightforward. With a collapsed AMOC, the heat transport that currently keeps Europe artificially warm in winter is gone. Westerly winds that once arrived loaded with Atlantic warmth would arrive cold, having crossed an ocean that no longer pumps heat from the tropics. Sea ice from the Arctic would expand southward, eventually reaching parts of Britain, Scandinavia, and the Netherlands. Sea ice reflects sunlight back into space, amplifying cooling, a positive feedback that intensifies winter chill year by year. Stefan Rahmstorff, the Potsdam oceanographer, called the study a confirmation of long-standing concern. The model, he said, validates fears that AMOK collapse would produce massive impacts on European temperature extremes. He added that passing the AMOK tipping point by mid-century looks increasingly likely in light of recent studies. 25 years from now, the Utrecht results are model projections, not predictions, and the researchers themselves emphasize the uncertainty. The exact temperatures depend on the emissions pathway, the precise timing of any AMOK collapse, the representation of sea ice in the model, and a dozen other variables. But the qualitative picture is robust across multiple independent studies. A collapsed AMOK means a much colder Europe. Oslo at -48 is one extreme. The mechanism that produces it, sea ice spreading where ocean used to be, is the next layer of the story. In the Utrecht simulation, one of the most jarring visual changes was not the temperature graphs, it was the maps. Year by year, in the model's AMOK collapsed future, white sea ice spread southward across the North Atlantic. By the end of the simulated century, the ice pack had reached areas of the ocean that no human has ever seen frozen in modern times. Parts of the British Isles, coastal Scandinavia, sections of the Dutch and German North Sea coasts. To understand why this matters so much, you have to understand sea ice as an active player in climate, not a passive one. Ocean water absorbs roughly 95% of the sunlight that hits it. The dark surface drinks in solar energy and converts it to heat. Sea ice does the opposite. It is white. It reflects somewhere between 50 and 90% of incoming sunlight, straight back to space. The technical name for this property is albedo. High albedo means high reflectivity. Sea ice is one of the highest albedo natural surfaces on Earth. When sea ice spreads, the part of the ocean that used to absorb sunlight now reflects it. The local heat budget collapses. The water beneath the new ice gets less sunlight, stays colder, and creates conditions for even more ice to form. The feedback is positive in the technical sense, meaning self-amplifying. A small initial expansion of ice produces conditions that drive further expansion. The system runs away. This is exactly the dynamic that the Utrecht model captured. In their simulation, the initial AMOC collapse caused some sea ice expansion. The expansion increased reflectivity, which increased cooling, which increased ice. Over decades, the ice pack reached down through latitudes that have not been frozen since the depths of the last ice age. Imagine standing on a beach in Brighton, on the south coast of England, in February. Today, the water is cold but liquid. People walk dogs. Surfers in thick wetsuits paddle out. In the AMOC collapsed scenario, the water in front of you would, in some years, be solid. Pack ice extending for miles offshore, foggy, frigid, and deeply alien to anyone who knows the modern British coastline. The implications go beyond temperature. Sea ice changes everything around it. Fisheries collapse because the species that supported them, cod, herring, mackerel, cannot survive under the new conditions. Shipping routes that have been open for centuries become seasonally blocked. Ports freeze over for months at a time. The Thames, which last froze solidly enough to support market fares in the early 1800s, would once again become a frozen highway in winter. The North Sea oil rigs would face conditions they were not designed for. The agricultural consequences would be catastrophic. Britain's wheat-growing regions are already at the cold edge of viability for many crops. Add a sea ice-amplified winter, multi-month frosts, frozen ground, late-arriving springs, and large portions of the British and Northern European agricultural belt would simply stop producing the grains they currently produce. Population centers built around year-round access to nearby food would face supply chain shocks no modern economy is structured to handle. There is one twist in the science worth noting. In the highest emissions scenarios, the sea ice spread is less dramatic. Why? Because so much warming has occurred globally that even the cooling effect of an AMOC collapse cannot overcome the heat already locked into the system. In other words, the worst sea ice expansion happens in mid-emissions worlds where the AMOC collapses but global warming has not yet overwhelmed the cooling. That makes the planning calculus deeply strange. Aggressive global warming might paradoxically prevent the British coast from freezing over. Moderate warming with an AMOC's collapse might produce the harshest winters in modern European history. For an entire continent, the difference between those two futures comes down to a single threshold no one can pinpoint precisely. But the cold spreading south is only half the climate paradox. The other half is what is happening to the rest of the planet, much of which is getting hotter, not colder. In exactly the same scenarios, climate change is, by definition, warming. The global average temperature is rising. Glaciers retreat. Ice caps shrink. Hot summers shatter records year after year. So the idea that one corner of the planet, Northern Europe, could actually become colder while the rest of the world bakes seems contradictory at first glance. It is one of the most counterintuitive findings in modern climate science. Yet, the physics is solid, and the reason comes down to the difference between global heat and regional heat distribution. Global warming heats the entire planet on average, but the climate system is not a single bowl of evenly stirred soup. It is a vast network of currents, winds, and pressure patterns that move heat from where there is too much to where there is too little. The AMOC is one of the most important pieces of that network. It takes excess tropical heat and ships it north. Without that shipping service, the tropics get even hotter, the Arctic gets locally colder, and the regions that used to receive the delivery, Northern Europe especially, sit in a strange thermal limbo. The Utrecht team's simulations made the paradox concrete. In a world warmed by 2 degrees Celsius globally, with an AMOC collapse, Northern Europe ends up colder than today, not slightly colder, substantially colder, with brutal winter extremes. Yet the same model shows the rest of the planet continuing to warm. Africa, South America, Australia, much of Asia, all hotter than they are now. Even Southern Europe ends up roughly as warm as today, perhaps slightly cooler in winter but still hotter in summer. The pattern looks like a climate map drawn by an indecisive artist. Most of the world reddened with heat, a blue patch over the British Isles, Scandinavia, and the seas around them. Almost looks like an error. It is not. The cause is the redistribution of heat. With the conveyor stalled, tropical heat that used to flow north stays trapped at lower latitudes. The southern hemisphere actually warms slightly faster than it would have without an AMOC collapse, because heat that used to be exported north now stays put. Meanwhile, Northern Europe loses its delivery, and the cooling effect of an expanding sea ice pack amplifies the local chill. There is a second factor. Atmospheric circulation responds to the new ocean state. Westerly winds carrying moisture and warmth across the Atlantic to Europe weaken or shift. The jet stream, which has its own complex dynamics linked to ocean temperature contrasts, may become more meandering, locking cold polar air over Europe for longer periods each winter. Some researchers have used the phrase climate scissor for this dynamic. One blade of warming, one blade of regional cooling, both swinging shut on Europe at the same time. The agricultural calendars, the water resources, the energy systems, all built around a stable middle climate, get sliced apart by the two opposing forces. A different scenario shows up in the high emissions pathway. If global warming reaches 4 degrees Celsius and the AMOC collapses, the warming wins. Northern Europe still warms, just more slowly than the rest of the planet. Sea ice does not spread as dramatically. Winters get harsher than today's, but not as harsh as in the moderate scenario. This is one of the more uncomfortable conclusions of recent modelling. Aggressive emissions reductions might increase the chance of a colder Europe rather than a warmer one, at least in the short term, because moderate global warming combined with amok collapse is the worst combination for European temperatures. Climate science rarely produces ironies that pointed, but this one is real, repeatedly produced across multiple modelling groups, and increasingly seen as the most plausible future for the continent. The ripples reach much further. Beyond Europe, the same redistribution of heat is set to break weather systems hundreds of millions of people depend on for their daily food. A few hundred miles north of the equator, a band of rising air circles the entire planet. Warm tropical air gets pushed up into the atmosphere by intense solar heating, releases its moisture as it rises, and feeds an almost continuous belt of clouds and rainfall, stretching from the Atlantic across Africa, the Indian Ocean, and into the Pacific. This band has a clinical name, the Intertropical Convergence Zone. To the people who live under it, it has another name, the monsoon. The position of this rain belt is not fixed. It migrates north and south with the seasons. Its summertime northward swing is what brings the rains to West Africa, India, Bangladesh, Indochina, and Southeast China. Its winter retreat brings the dry season. Billions of people have built entire civilizations around the predictable rhythm of those movements. The AMOC controls the rhythm. Here is the link. The conveyor delivers heat to the northern hemisphere. That asymmetric heat transport, more warmth on top, less below, keeps the rain belt biased slightly north of the geographic equator. If you weaken the AMOC, you remove that northward bias. The rain belt drifts south. It still rains under the belt, but the belt is no longer over the same farms, the same villages, the same rivers it has been over for thousands of years. Multiple climate models converge on this prediction. A weakened or collapsed AMOC causes a southward shift of the tropical rain belt by hundreds of miles. The exact magnitude depends on the severity of the AMOC change and the modelling approach, but the direction is robust across studies. For West Africa, the consequences would be severe. The Sahel, the semi-arid band stretching across Senegal, Mali, Burkina Faso, Niger, and Chad, sits at the northern edge of the modern rain belt. The region has experienced devastating droughts in the 1970s and 1980s, partly linked to natural AMOC variability. A sustained AMOC weakening would push the Sahel deeper into permanent drought conditions, with far less of the seasonal monsoon rain reaching its fields. Sorghum, millet, and maize harvests across the region would face long-term collapse. A 2025 image from drought-affected areas of Kenya circulated widely in climate coverage. People loading water containers onto donkeys, walking miles to dwindling sources. That scene becomes more common, not less, in an AMOC-weakened world. South Asia faces a different kind of disruption. The Indian monsoon is more directly tied to the temperature contrast between the warm Indian Ocean and the cooler land of the subcontinent. AMOC weakening affects this through complex pathways involving sea surface temperatures and atmospheric circulation. Most projections suggest the Indian monsoon would weaken on average, with greater year-to-year variability, meaning some years would still bring normal rainfall, but failed monsoon years would become far more frequent. For a country whose agriculture is largely rain-fed, where roughly 600 million people depend on monsoon-dependent farming for their livelihoods, the variability alone would be devastating. Crop insurance systems, food distribution networks, and rural economies are not built to absorb repeated bad years. Southeast Asian rice production faces similar stress. The monsoon timing controls rice planting, growth, and harvest cycles across Vietnam, Thailand, Cambodia, and parts of Indonesia. Disruption to that timing, even without total monsoon failure, can cut yield significantly. The geopolitical implications stretch beyond food. When agriculture fails on the scale modelled, populations move. The displacement could reach hundreds of millions of people across decades, putting pressure on borders, cities, and political systems that already struggle to manage current migration flows. The 2007 to 2010 Syrian drought, which preceded the country's civil war, has been studied as an early example of climate-driven instability. A sustained AMOS-induced shift in tropical rainfall would dwarf that scale of disruption many times over. There is one geographic region where the rain belt shift produces an unexpected effect, and it sits in the middle of South America. The Amazon rainforest may end up doing something nobody predicted. The Amazon basin is the largest rainforest on Earth. It covers roughly 2.5 million square miles across 9 countries. It produces an enormous fraction of the planet's biodiversity, stores more carbon than any other terrestrial ecosystem, and exerts measurable influence on global climate through its evapotranspiration. Climate scientists have long worried that a hotter, drier future could push the Amazon toward dieback, a transition from rainforest to savanna that would release massive amounts of carbon and devastate biodiversity. Then a 2021 modeling study added a strange wrinkle to the story. The researchers ran simulations to explore what would happen to the Amazon under an AMOC collapse combined with continued warming. The expected result, given the general drying tendency of climate change, would be a worsening of the Amazon dieback risk, a weaker conveyor, a hotter planet, a drier rainforest. That is not what the model showed. Instead, the AMOC collapse triggered a southward shift of the intertropical convergence zone, the same shift that hurts Africa and South Asia. But for the southern Amazon, that shift means the rain belt now sits more directly overhead. Rainfall in the southern Amazon increased in the simulation, partly counteracting the drying caused by warming. The result, according to the 2021 study, was that an AMOC collapse could actually help stabilize the southern part of the rainforest, reducing the risk of dieback in that region, a counterintuitive outcome from a system that produces almost nothing but bad news. The catch, of course, is that helping one region of the Amazon does not save the whole rainforest. The northern Amazon receives the opposite signal: less rain, more stress. So one part of the forest gets a partial reprieve, while another part suffers more. A 2024 study added even stranger detail. With a collapsed AMOC, the seasonal cycle of the Amazon could effectively reverse. Wet seasons might become dry, dry seasons might become wet. The shift would not change the total amount of rain dramatically, but it would change when the rain falls. For ecosystems that have evolved over millions of years to match a particular seasonal rhythm, that is a massive disruption. Tree species, insects, fish, birds, and the indigenous communities living within the rainforest all depend on the timing of the wet season for reproduction, migration, and food supply. Imagine a city scheduling its garbage collection on an entirely random day of the week. The total amount of waste collected stays the same, but every system built around the old schedule breaks. The Amazon's biological clocks operate on rainfall, timing the way a city operates on calendar weeks. Reverse the seasons, and even small changes in total precipitation become catastrophic for the species fitted to specific timings. The AMOC's reach into the deepest tropical ecosystems on the planet illustrates something important about ocean currents. They are not just water moving in circles, they are control levers for nearly every major weather pattern on Earth. Pull on one lever in the North Atlantic, and a forest in Brazil rearranges its own seasons. In response, the Amazon story also highlights why predicting AMOC consequences is so difficult. Some impacts are dramatic and obvious. A colder Britain, a flooded Norfolk. Others are subtle, regional, and often counterintuitive. Climate models are improving rapidly, but the full set of consequences remains partially unknown. New surprises keep emerging from each round of higher resolution simulations. What is not subtle is the impact already occurring along the United States East Coast. The slowdown is no longer a future scenario for that stretch of coastline. It is a present tense reality. Sea level rise is not uniform. The popular image of a globally rising bathtub does not capture how the actual ocean behaves. Different coasts rise at different rates, depending on local geology, ocean currents, gravitational effects from melting ice, and several other factors. For most of the world's coasts, the regional rate is within a few inches of the global average. For the northeastern United States, the regional rate is much higher. Tide gauges along the east coast, some of which have been operating for over a century, show sea level rising roughly twice as fast as the global average, from Cape Hatteras north to Nova Scotia. The acceleration has been particularly strong since the year 2000. Some sites have logged annual increases that scientists once predicted for the year 2050. A growing body of research connects this regional anomaly directly to the AMOC. The mechanism, as introduced earlier in this script, involves the Gulf Stream's role in pulling water away from the east coast. A strong, well-positioned Gulf Stream creates pressure dynamics that hold sea level along the coast slightly lower than it would otherwise be. As the Gulf Stream weakens and shifts north, that suction effect weakens. Water that used to flow away from the coast now piles against it. The result is local sea level rise on top of whatever the global ocean is doing. A 2025 study by United States federal climate researchers, mentioned earlier, found that AMOC weakening contributed to as much as 50% of flooding events along the northeastern coast since 2005. That number is worth pausing on. It means half of the so-called nuisance floods, sunny day floods, and minor storm surges that residents of New York, Philadelphia, Baltimore, Norfolk, and Boston have experienced in the past 2 decades trace back, at least in part, to a single global ocean current weakening on the other side of the Atlantic. The economic costs are mounting. Coastal infrastructure is corroding faster than expected. Roads that lasted 30 years now need replacement after 15. Storm drains designed to handle occasional inundation now corrode from chronic salt exposure. Property insurance markets are pulling out of certain zip codes. Some coastal real estate, particularly in Miami Beach and parts of the New Jersey shore, has begun losing value relative to inland properties. An economic signal that markets are pricing in the rising risk faster than government policy is responding to it. A 2026 projection that combined AMOC weakening with continued global ocean rise estimated that the East Coast could see an additional 6 to 12 inches of regional sea level rise by 2100 on top of the global average. That additional foot, when applied to existing coastal topography, transforms what is currently considered a 100-year flood event into something that happens every few years. For specific cities, the consequences have already crossed from theoretical to operational. Norfolk has spent billions on coastal defense projects. New York City completed major flood barriers in Lower Manhattan after Hurricane Sandy and continues to expand them. Charleston has been raising entire streets to keep them above expected high tides. Miami Beach has installed pumps to push water out of streets during king tides, pumps that were not needed 20 years ago. The political response has been mixed. Some communities have started planned retreats, buying out homeowners in the most vulnerable zones and converting the land back to wetlands. Others have doubled down on defending current shorelines with seawalls and surge barriers. Both strategies are expensive. Both involve difficult choices about who pays and who bears the loss. Slowing, drifting, pulling its hands off the East Coast year by year, allowing the water to creep up. The conveyor, which has shaped European climate for centuries, is now also shaping the daily lives of millions of Americans. The same conveyor influences the weather systems forming over the warm Atlantic each summer, and the connection between AMOC weakening and Atlantic hurricanes is one of the more debated areas of current climate research. Hurricanes are heat engines. They form over warm tropical ocean water, draw energy from sea surface temperatures, and release that energy as wind, rain, and storm surge when they make landfall. Anything that changes the temperature of the tropical Atlantic changes the conditions under which hurricanes are born and grow. The AMOC, by redistributing heat, has direct influence on those temperatures. The relationship is more complicated than a simple weaker AMOC means stronger hurricanes. Different parts of the hurricane life cycle respond to different aspects of ocean temperature. Some studies suggest a weaker AMOC could lead to more intense hurricanes. Others suggest fewer hurricanes overall, but with more rapid intensification. A few suggest the storm tracks themselves could shift, exposing different coastlines to greater risk. The basic physics works like this. When the AMOC slows, heat that normally moves northward stays trapped in the tropical Atlantic. Sea surface temperatures in the hurricane main development region, a swath of warm water between Africa and the Caribbean, could rise above current levels. Hurricanes drawing energy from that warmer water could form more easily and grow more powerful. But the AMOC also affects the wind shear pattern over the Atlantic. Wind shear is the change in wind speed or direction with altitude. High shear tiers developing storms apart before they can organize. Low shear allows them to grow. AMOC-driven changes in atmospheric circulation could alter shear patterns in ways that either favor or suppress hurricane formation, depending on the region and season. Recent research has tried to disentangle these competing effects. A 2024 modeling study found that under an AMOC collapsed scenario, the total number of Atlantic hurricanes might actually decrease modestly, but the average intensity would increase. The fewer storms that did form would be more likely to reach Category 4 or 5 levels and would intensify more rapidly than current storms typically do. Rapid intensification is one of the most dangerous aspects of modern hurricanes. A storm that goes from Category 1 to Category 4 in 24 hours gives coastal communities far less time to evacuate. The 2018 Hurricane Michael, the 2017 Hurricane Maria, and the 2024 Hurricane Helene all featured periods of rapid intensification that caught forecasters and residents off guard. Climate research increasingly suggests these events are becoming more common. AMOC changes alter the position of the Bermuda High, a semi-permanent atmospheric feature that helps steer hurricanes. A different Bermuda High position means hurricanes follow different paths. Some studies suggest that under AMOC weakening, more storms could curve north along the east coast rather than following more westerly paths into the Gulf of Mexico. That would shift hurricane risk away from Texas and Louisiana toward the Carolinas, the Mid-Atlantic, and even New England. The historical record contains hints. The 1938 New England hurricane, which devastated Long Island and the Connecticut coast, was an extreme outlier for its time. Some climate historians have argued that periods of natural AMOC weakening in the past correspond to anomalous hurricane tracks. If so, the modern AMOC slowdown could be increasing the probability of similar surprises. For coastal property markets, insurance systems, and emergency management agencies, the implications are significant. Risk maps based on 20th century hurricane behavior may not reflect 21st century reality. Buildings constructed to handle Category 2 or 3 storms may be hit by Category 4S. Cities that have rarely faced direct hurricane impacts may need to prepare for them. The hurricane connection is one of the more uncertain aspects of AMOC consequences. Different models produce somewhat different results. The signal is real but harder to pin down than the European cooling or East Coast flooding signals. What is clear is that any major change in the Atlantic conveyor will affect the storms that form over Atlantic waters. The only question is exactly how. There is one scientific question that has emerged as a potential counterweight to all the bad news: whether another current somewhere else might compensate for an Atlantic collapse. In April 2025, a Nature paper landed in the AMOC literature with a slightly different message than most recent work. The lead author was Jonathan Baker, and the paper analyzed 34 climate models running under extreme greenhouse gas and freshwater forcing scenarios. The question the team asked was simple. Even under the worst-case forcing, would the AMOC actually collapse to zero, or would something else step in? A different current. The Pacific Meridional Overturning Circulation. The Pacific Meridional Overturning Circulation, or PMOC, is a hypothetical sister system to the AMOC. In the present-day climate, it does not really exist as a strong feature. The Pacific Ocean does have circulation, but its overturning behavior at northern latitudes is weak compared to the Atlantic. Salinity in the North Pacific is too low for major sinking to occur. The conveyor pattern that defines the AMOC has no real counterpart on the other side of North America. Baker's team found that in their 34-model ensemble, when extreme forcing weakened the AMOC severely, a PMOC consistently emerged. Not a strong one, but a real one. The Pacific developed enough overturning to partially compensate for what the Atlantic was no longer doing. The result, in the models, was an AMOC that weakened dramatically but did not fully collapse, because the global ocean system found a different way to balance itself. The mechanism involves the Southern Ocean, wind-driven upwelling in the Southern Ocean. Strong westerly winds that pull deep water up to the surface must be balanced by sinking somewhere. In the present climate, most of that balancing happens through the AMOC's deep water formation in the North Atlantic. But the Southern Ocean upwelling is not going to stop. The winds keep blowing. So if the AMOC fails to provide the sinking, the system has to find another sinking site. The North Pacific, in the model results, becomes that site. Baker's interpretation was that the AMOC alone might not be able to fully collapse in this century because the global circulation system has built-in stabilizing mechanisms. A PMOC develops in nearly all of the models tested. The total collapse some early studies feared may not be possible without a complete rearrangement of the global ocean. The findings were greeted with cautious optimism in some quarters and significant skepticism in others. Stefan Rahmstorff, the Potsdam oceanographer, was among those who pushed back. He noted that even if a PMOC develops, the timescales involved may be very long. The Pacific compensation might take centuries to fully kick in, while the AMOC weakening happens much faster. In the gap between AMOC weakening and PMOC compensation, the climate impacts on Europe, the East Coast, and the tropical rain belt would still occur. The PMOC arriving eventually does not save anyone living through the transition. There is also a question of whether the models accurately capture all the relevant physics. Several oceanographers have argued the freshwater sensitivity of the AMOC is higher than most models suggest, particularly when realistic Greenland melt is included. If the AMOC can collapse faster than the models predict, the PMOC compensation might not develop in time to maintain anything like the current heat distribution. Another concern is the location of the new sinking site. PMOC sinking would happen in the North Pacific, far from the regions that depend on AMOC heat transport. A PMOC redirects heat into the Pacific Basin and the Arctic via a different pathway than the AMOC does. Europe and the North Atlantic do not benefit from a Pacific replacement. They still lose their heat delivery. The PMOC theory is not a relief from AMOC concerns. It is a complication. It suggests the global ocean system is more resilient at the planetary scale than at any single regional scale. The AMOC region, the European climate, the East Coast, could still suffer catastrophic disruption even if the rest of the global ocean rebalances. The conveyor that matters to Europeans is the Atlantic one, and that one is in trouble whether or not the Pacific eventually steps up. The more the Southern Ocean is examined, the more central it becomes to the entire question of AMOC stability. The Southern Ocean is the body of water that wraps around Antarctica. It is the only ocean that fully encircles the globe, with no continents to interrupt its flow. Strong westerly winds, sometimes called the Roaring Forties and Furious Fifties, blow eastward across this ocean almost continuously. Those winds, combined with the geometry of an unbroken ocean, create some of the most powerful and consistent ocean dynamics on Earth. For a long time, the AMOC story was told as if the North Atlantic were the only thing that mattered. The conveyor sank up north, returned south through the deep, and that was that. Recent research has shifted focus dramatically. The Southern Ocean is now understood to be at least equally important. In some framings, it may be more important. The reason is upwelling. Deep water that has been hidden from the surface for centuries gets pulled back up to the sunlit zone, primarily in the Southern Ocean. driven by the relentless westerly winds. Those winds blow north of the Antarctic circumpolar current, dragging surface water away from the Antarctic continent. Deep water rises to fill the gap. This process is called wind-driven Ekman upwelling, and it pulls roughly the same volume of water up as the AMOC sinks down on the other side of the planet. This connection means the AMOC and the Southern Ocean upwelling are linked at the planetary scale. They are two halves of the same global circulation, even though they sit oceans apart. What happens at one end constrains what happens at the other. This is the foundation of the Pacific compensation argument from the previous chapter. If the Southern Ocean keeps upwelling and the AMOC fails to balance it, something else has to. The PMOC steps up. The system rebalances. The Southern Ocean's behavior may also be a key factor in determining how stable the AMOC is in the first place. A 2025 paper in Nature by Baker and colleagues argued that as long as the Southern Ocean winds remain strong, the AMOC cannot fully collapse, because the upwelling demands a sinking partner somewhere, and the North Atlantic is the most efficient available site. Weaken Southern Ocean winds, and the constraint loosens. Strengthen them, and the AMOC is held together by the global pattern, even when freshwater forcing pushes it hard. What is happening to Southern Ocean winds in the modern climate? The picture is mixed. Some research suggests the winds are intensifying, partly due to the changing temperature gradient between Antarctica and the warming mid-latitudes. Stronger winds would mean more upwelling, which would in turn keep pressure on the AMOC to maintain its sinking. That sounds like good news for AMOC stability. But other research highlights complications. The strengthened winds also lead to increased eddy activity in the Southern Ocean, which can partially cancel the upwelling effect through a phenomenon called eddy compensation. The net effect on global circulation is not yet clear. Different models produce different answers. There is also the question of Antarctic ice. Antarctica is shedding mass, though more slowly than Greenland. As Antarctic meltwater enters the Southern Ocean, it can disrupt local circulation patterns and affect the water masses that ultimately influence global overturning. The Antarctic and Greenland melt stories are connected, even though they happened at opposite ends of the planet. Some researchers have started arguing that the long-term fate of the AMOC will be determined as much by what happens around Antarctica as by what happens around Greenland. The two polar regions are coupled through the global ocean. Ignoring one while obsessing over the other produces an incomplete picture. The Southern Ocean's role complicates the early warning conversation. If the AMOC stability depends partly on Southern Ocean winds, then monitoring those winds becomes essential. If the strength of the AMOC's response to freshwater forcing depends on what is happening in the Antarctic, then Greenland-only forecasting is not enough. Climate science is increasingly a planetary-scale endeavor. The Atlantic conveyor cannot be understood without the Southern Ocean. The Southern Ocean cannot be understood without the Atlantic. The ice melts in Greenland and Antarctica are linked. The tropical rain belt responds to forcing from both poles. To predict where the AMOC is going, scientists are essentially trying to forecast the future of the entire global ocean and the atmosphere above it. That is an enormous task, and one of the most direct tests they have come up with is to deliberately try to break the AMOC inside their computer models. When climate scientists want to know how a system responds to extreme conditions, they sometimes do something that sounds counterintuitive. They try to break the system, inside computer models, of course. Not in the real ocean. The technique is called freshwater hosing, and it has become one of the most important tools for understanding the AMOC's behavior under stress. The basic idea is simple. Take a working climate model. Add a large input of fresh water to the North Atlantic, simulating an extreme melt event from Greenland or beyond. Watch what happens to the AMOC. Try different amounts. Try different durations. Try different starting conditions. See where the system breaks and where it bends. The first hosing experiments date back to the 1980s, when scientists were just beginning to understand the AMOC's Bistability. Early experiments confirmed what theory predicted. Add enough fresh water, and the conveyor weakens or collapses. The exact threshold varied across models, but the general behavior was consistent. Modern hosing experiments have become far more sophisticated. The North Atlantic Hosing Model Intercomparison Project, completed in 2023, tested 8 different climate models from 6 modeling centers. The team applied a standardized freshwater input, 0.3 sverdrops, sustained for several decades, and compared how each model responded. The results were instructive. About half of the models showed the AMOC recovering after the hosing ended. The other half did not recover. The AMOC stayed in a weakened state long after the freshwater input stopped, even when the original conditions were restored. This bifurcation of model behavior is exactly what Bistability predicts. Some models, with their specific physics and parameters, sat in conditions where the AMOC could rebound from the freshwater shock. Other models sat closer to the tipping point and got pushed across it. Once across, the same feedbacks that previously stabilized the strong state now stabilized the weak state. The marble had jumped the ridge. The implication for the real Atlantic is uncomfortable. We do not know precisely where the modern AMOC sits relative to its tipping threshold. Some indicators suggest it is close. Other indicators suggest it has more buffer. The hosing experiments do not tell us where the real-world threshold is. They tell us that the threshold exists and that crossing it produces a long-term lock-in to a different state. A 2024 hosing study went further. The team applied freshwater forcing to a model and monitored a specific physical quantity, the freshwater transport at the southern boundary of the Atlantic. They found that the metric reliably indicated when the AMOC was approaching collapse, even before the collapse itself became visible in standard measures of conveyor strength. This metric is the one that led to the headline conclusion that the AMOC is en route to tipping. The team identified a measurable real-world indicator that could function as an early warning, similar in spirit to the Gulf Stream shift, but applied to the southern end of the basin rather than the north. Other early warning indicators have been proposed. Variance in AMOC strength tends to increase as the system approaches a tipping point, a phenomenon called critical slowing down, observed in many bistable systems across physics and ecology. Autocorrelation in the time series of AMOC measurements also increases. Both metrics have been calculated for the available observational data, and both show patterns consistent with an AMOC moving closer to its tipping point. These findings are not universally accepted. Some researchers argue the available observational record is too short to reliably detect critical slowing down. Others note that the early warning indicators in the proxy reconstructions of AMOC strength, which extend back farther than direct measurements, may suffer from data quality issues that make the signals unreliable. The debate in this corner of the field is intense and ongoing. What everyone agrees on is that the questions matter. If reliable early warning indicators can be developed, humanity gains decades of advance notice before catastrophic collapse. If the indicators are illusions or false positives, we may continue to assume time we do not actually have. The disagreements among scientists about timing and severity are not academic squabbles. They are the central uncertainty driving every conversation about how seriously to treat the AMOC threat right now. Open the most recent comprehensive assessment from the Intergovernmental Panel on Climate Change, the global scientific consensus body on climate change, and you will find a calm, measured statement about the AMOC. The conveyor will very likely weaken during the 21st century. An abrupt collapse before 2100 is not expected, with medium confidence. The language is hedged. The implication is that policymakers should worry about gradual slowdown, but not about catastrophic collapse anytime soon. Now read a recent study from the Niels Bohr Institute, Utrecht University, or the Potsdam Institute. Different message. AMOC could be approaching tipping point, possible collapse by mid-century. Real-world observations validate the most pessimistic projections. The framing is much more urgent. Why the gap? Part of the explanation is timing. The IPCC's assessments are based on the literature available at the time of writing. The sixth assessment report's main contributions were drafted in 2020 and 2021, with publication in 2021 and 22. Since then, a wave of new research has emerged with significantly different conclusions. The 2023 hosing experiments, the 2024 Science Advances paper on tipping indicators, the 2025 University of Miami Observational Study, the 2026 Portman projection paper, the 2026 Utrecht Gulf Stream paper. None of these were available when the IPCC was writing. The IPCC essentially reflects 2021 understanding. The current scientific frontier reflects 2026. 5 years matters when the field is moving fast. A second factor is the IPCC's institutional caution. The body operates by consensus and avoids language that could be perceived as alarmist. When the underlying science is uncertain, the IPCC tends to err toward conservative phrasing. This is generally appropriate for a global authority making policy-relevant statements, but it can produce significant lag between scientific findings and IPCC pronouncements, especially in areas of active controversy. A third factor is the particular models the IPCC relied on. As Portman's 2026 paper and others have shown, standard climate models share systematic biases that cause them to underestimate AMOC weakening. The IPCC's AMOC projections were largely based on these models. Corrected projections give darker results. The IPCC has acknowledged some of these issues, but has not yet revised its main AMOC statements to reflect them. A fourth factor involves what the IPCC was even trying to estimate. The sixth assessment report focused on the probability of an abrupt collapse by 2100. The newer studies are often discussing a tipping point being crossed by 2100, with the actual collapse occurring decades or centuries later. The two questions are different. A tipping point can be crossed in a particular year, with the catastrophic consequences only fully manifesting in a later year, when the system has fully reorganized. The IPCC's assessment that abrupt collapse is not expected before 2100 inches is technically compatible with a tipping point being crossed by 2050. The newer studies focus on the tipping point crossing as the policy-relevant moment, since after that point, the collapse becomes essentially unstoppable. A fifth factor is that some scientists genuinely believe the newer studies are overstating the case. The 2025 Nature paper by Baker and colleagues, which argued that Southern Ocean upwelling effectively prevents total AMOC collapse, falls into this camp. There are reputable researchers who think the AMOC is more resilient than the recent alarming results suggest. The science is not unanimous. Reasonable disagreement exists. The result of all this is a public-facing confusion. A reader of mainstream news might encounter an article saying the AMOC is on the verge of collapse, followed a week later by an article saying climate models suggest the AMOC will be relatively stable through 2100. Both articles are reporting on real research. Both are correct in some sense. The disagreement is real and reflects genuine scientific uncertainty about the timing and severity of AMOC weakening. What is not in dispute is that the AMOC is weakening. Direct observations confirm that. What is not in dispute is that continued weakening will produce significant climate consequences. What is not in dispute is that the system has the capacity to tip into a fundamentally different state. The disagreements are about how close we are to the tipping point and how confident we should be in projections of when it might be crossed. For policymakers, the practical implication is to plan for adaptation and mitigation under significant uncertainty. The worst-case scenarios are credible enough to take seriously. The best-case scenarios are not so reassuring as to permit complacency. Stefan Rahmstorff has been quoted saying that the situation increasingly looks like a 50-50 chance the tipping point is crossed by mid-century. That is not a confident prediction, but it is also not a comfortable one. The question that keeps surfacing in private conversations among ocean scientists is whether the threshold has already been crossed, without anyone realizing it. Tipping points have a strange property. By definition, they are the moment when a system commits to a new state. but the commitment becomes obvious only in retrospect. While the system is still gradually shifting toward the threshold, behavior can look similar to the system bouncing around its old equilibrium. Only after the threshold is crossed and the new dynamics take hold does the change become unmistakable. By then, the moment of decision is years or decades in the past. This raises an uncomfortable possibility for the AMOC. The tipping point may have already been crossed. We may already be living in a world where the conveyor is locked into a path of eventual collapse, even though the collapse itself is still decades away. We would not know because the immediate signals look indistinguishable from a system that is weakening but still recoverable. Some indicators suggest exactly this scenario. The 2024 Science Advances paper that introduced the freshwater transport metric for tipping indicators ran the metric on observed data and concluded the AMOC is en route to tipping. The phrase has been carefully scrutinized. It does not say the tipping has already occurred. It says the trajectory points toward tipping. The implication is that without changes in the forcing, primarily reductions in freshwater input from melting ice, and reductions in greenhouse gas emissions, the trajectory will reach the threshold. Whether reductions are even possible at the necessary scale is a separate question. Greenland's melt rate is determined by factors that cannot be quickly reversed. Greenhouse gas reductions, even if achieved aggressively, do not immediately stop ice melt. The thermal inertia of the climate system means warming continues for decades after emissions stop. So even an optimistic scenario for emissions reductions does not guarantee that AMOC's freshwater forcing decreases on timescales relevant to preventing tipping. A 2023 study by Peter Ditlevsen and Suzanne Ditlevsen, published in Nature Communications, used statistical analysis of sea surface temperature reconstructions to estimate when the AMOC tipping point might occur. Their central estimate placed it around 2057, with a confidence interval extending from 2025 to 2095. That estimate was widely covered in popular media and widely critiqued by other AMOC researchers. The methodology has limitations. The reconstructions used are imperfect. The statistical assumptions may not hold. But the paper raised the disturbing possibility that we could be inside the window already. If the Ditlevsen study is correct, the tipping could happen at any time between now and 2095, with the median estimate being closer to mid-century than to the end of the century. That is not a comforting framework. It means we cannot rule out crossing the threshold within the next decade. We cannot confidently declare that we have decades to prepare. The 2026 Utrecht Gulf Stream paper added another layer to this concern. The paper showed that abrupt Gulf Stream displacement occurs roughly 25 years before AMOC collapse. The current observational evidence shows the Gulf Stream is in its Phase 1 slow drift, but the abrupt Phase 2 leap has not been clearly observed yet. If the leap occurs, it would indicate the AMOC has crossed an internal threshold from which collapse follows roughly a quarter century later. Researchers monitoring the Cape Hatteras crossover position are essentially watching for this trigger. The fact that the trigger has not fired yet is reassuring on one level. The Phase 2 leap appears to be a discrete event, and we have not yet seen it. That suggests the tipping has not yet occurred, but the Phase 1 drift is well documented. The drift has been steady for at least 3 decades. At some point, by the model's own logic, the drift transitions to a leap. The model cannot tell us exactly when. The transition is determined by the specific physics of the deep current, the salinity field, and the freshwater input, all of which are evolving in real time. The honest scientific answer to the question of whether the tipping point has already been crossed is that we do not know. The data we have is consistent with both possibilities. The next decade of measurements will be critical for narrowing the uncertainty. By the early 2030s, the picture should be much clearer. Whether that clarity will arrive in time to take meaningful action, if action is even possible, is a separate question. For now, the AMOC sits in a state of unresolved suspense, slowing, drifting, possibly already past the point of no return, possibly still recoverable? The science cannot say. And while the science argues, the consequences for one of the most basic features of the North Atlantic, the food web that supports its fisheries, are already starting to show. The North Atlantic feeds people. It always has. From the cod fisheries of Newfoundland that drove European exploration of North America, to the herring shoals that built the wealth of medieval Hanseatic ports, to the modern industrial fisheries that supply protein to hundreds of millions of consumers, the Atlantic has been one of the most productive food-producing regions on Earth for as long as humans have been fishing. That productivity rests on a foundation almost nobody sees: plankton. Plankton are the microscopic organisms that drift in the upper ocean. Phytoplankton, the plant-like ones, perform photosynthesis using sunlight. Zooplankton, the animal-like ones, eat the phytoplankton. Small fish eat the zooplankton. Larger fish eat the smaller fish. Up the food chain it goes, all the way to tuna, cod, sharks, seabirds, and the dinner tables of cities thousands of miles inland. The whole pyramid sits on plankton. Plankton populations depend on nutrients: nitrogen, phosphorus, iron, silica. These nutrients enter the surface ocean primarily through deep water mixing. Cold, nutrient-rich water from below rises to the surface, fertilizes the sunlit zone, and triggers phytoplankton blooms. The blooms feed the entire ecosystem above. The AMOC is one of the major drivers of that mixing. Deep water sinking near Greenland, deep water rising elsewhere, currents transporting nutrients across the basin. The Atlantic conveyor is essentially a global stirring mechanism that keeps the nutrient supply active. A weakened AMOC means weakened mixing. Weakened mixing means less fertilization. Less fertilization means smaller plankton populations. Smaller plankton populations means a starved food web. A 2005 paper made the calculations. Severe disruption of the AMOC would cause North Atlantic plankton biomass to collapse to less than half of normal levels. The cause is a more stratified ocean, meaning the surface and deep layers do not mix as readily, combined with reduced nutrient exchange between layers. A halving of plankton would propagate up the food chain rapidly. Small fish populations would crash within a few years. Larger predator fish would crash in a decade or two. Seabird populations dependent on small fish would collapse. Whale populations dependent on plankton-feeding krill would shrink. The entire structure of the North Atlantic ecosystem, built up over millennia of stable productivity, would unravel. The consequences for the global fishing industry would be enormous. The North Atlantic provides a substantial fraction of the world's wild-caught fish. Iceland, Norway, the United Kingdom, Spain, France, Portugal, Canada, the United States, all have economies and food cultures heavily dependent on Atlantic fish. A collapse in productivity would force fleets to either travel farther for fish or find different occupations. Coastal communities built around fishing would lose their economic base. There is also a feedback into climate itself. Phytoplankton remove carbon dioxide from the atmosphere through photosynthesis. When they die, much of their carbon sinks to the deep ocean and is stored there for centuries. This is one of the most important natural carbon sinks on Earth. A collapse in plankton populations would weaken this sink, leaving more carbon dioxide in the atmosphere and intensifying global warming. The AMOC's effects on plankton create a positive feedback that could accelerate climate change beyond what direct emissions alone would produce. Some early signs of plankton stress are already visible. Long-term plankton sampling programs in the North Atlantic, like the Continuous Plankton Recorder Survey, have documented shifts in species composition and timing of blooms over recent decades. Some of these changes have been linked to ocean warming and acidification, rather than AMOC weakening directly, but the trends are consistent with a system under increasing stress. Fishing communities in places like Newfoundland and northeastern Scotland have noted changes in catch composition for years. Cod populations that once supported entire towns have not recovered to historic levels even after fishing pressure was reduced. Other species have moved in or out of traditional fishing grounds. The relationships between these changes and the AMOC are complex, but the broad picture is of an ecosystem in transition rather than at equilibrium. If the AMOC continues to weaken, these trends will accelerate. The question is not whether North Atlantic fisheries will be affected. They are already being affected. The question is how much further the productivity will decline and what social and economic systems will adapt or fail in response. The food web disruption is one piece of a larger picture. When ocean changes affect food supply, populations move. When populations move, political systems strain. Conflicts emerge. When climate scientists describe AMOC collapse, they often focus on physical impacts: colder Europe, sea level rise, tropical drought, plankton collapse. These are the direct measurable consequences. But behind every physical impact sits a human one, and the human consequences of an AMOC failure could reshape geopolitics in ways that might exceed the physical disruption. Start with food. The combination of failed monsoons in West Africa and South Asia, reduced agricultural output in Northern Europe, sea level rise flooding rice deltas in Bangladesh and Vietnam, and disrupted Atlantic fisheries would push global food supply chains into crisis. The world produces enough food today to feed everyone, even though distribution problems prevent it from doing so equitably. Take 10 or 20% of global food production offline simultaneously, and the math becomes much harder. Prices rise. Hunger spreads. The Arab Spring of 2010 to 2011, while caused by many factors, was preceded by a global spike in wheat prices driven partly by drought in Russia. That single year of disrupted supply contributed to political upheavals across the Middle East and North Africa. An AMOC-induced food crisis would not be one bad year. It would be decades of compounded stress. Migration follows food. When agriculture fails, populations move. The displacement potential from AMOC consequences is large enough that no current immigration system anywhere in the world is built to handle it. West African farmers losing their seasonal rains would not stay in place to die. They would move. The Sahel to Europe migration corridor, already under significant pressure, would face flows orders of magnitude larger than current ones. South Asian populations displaced by failed monsoons or coastal flooding would seek refuge wherever they could reach. Political responses to mass migration tend to harden over time. Countries close borders, walls rise, coast guards intercept boats. Domestic politics shifts toward anti-immigration parties and policies. The European Union has already faced significant strain from Mediterranean migration in the 2010. The strain from AMOC-driven displacement would be qualitatively different in scale. There is a darker possibility. Some commentators have noted that authoritarian regimes might calculate strategic advantage from coming climate disruption. Russia's geographic position with vast land area at high latitudes could make it relatively less affected by some AMOC consequences, and even potentially benefit from agricultural expansion northward, as warming opens new growing zones. Whether this calculation has ever explicitly entered Russian foreign policy is unknowable. But the strategic implications of climate change for a country like Russia, Canada, or the Nordic states are real and increasingly discussed in defense circles. China faces its own complex calculations: failed monsoons in the south, drought in the north, sea level rise threatening coastal megacities like Shanghai. The geopolitical positioning of a China facing severe internal climate stress could be unpredictable. The United States is in an unusual position. Direct AMOC effects on the US are mixed. The East Coast suffers from accelerated sea level rise, but the rest of the country may experience relatively less disruption than Europe or the tropics. American agriculture, while affected by climate change broadly, may be less directly threatened by AMOC consequences than agriculture in many other regions. This asymmetry could make the United States a relatively stable destination amid global instability, drawing more migration pressure to its borders. International institutions designed to manage cross-border challenges are not currently equipped for AMOC-scale disruption. The United Nations Refugee Framework, the World Trade Organization, the World Bank, the International Monetary Fund, all are products of a relatively stable mid-20th century world order. Whether these institutions can adapt to manage climate-induced disruption at the necessary scale is uncertain. There is also the question of whether climate disruption could trigger conflicts directly. Water-sharing disputes between India and Pakistan, between Egypt and Ethiopia, between Israel and its neighbors, could escalate if shared water resources become scarcer. Resource conflicts in the Arctic, where ice retreat is opening new areas to economic activity, are already increasing. The Russian invasion of Ukraine in 2022 demonstrated that major power conflict is not a relic of the 20th century. Climate-driven instability could increase the probability of similar conflicts elsewhere. These outcomes are not inevitable. They are scenarios that become more probable if the AMOC weakens severely or collapses. Aggressive climate mitigation, adaptation investment, international cooperation, and institutional reform could substantially reduce the risks. But the political will for such measures has so far been limited. The geopolitics of an AMOC failure may already be partially baked in. The recognition of these risks has prompted some scientists to consider truly radical interventions, including engineering proposals that would have been considered science fiction a decade ago. In 2024, a research team published a paper that briefly went viral in climate circles. The paper proposed building a massive dam between Alaska and Russia, across the Bering Strait, to prevent AMOC collapse. The idea sounded so preposterous that many readers initially assumed it was satire. It was not. The paper was a serious scientific contribution, exploring an extreme geoengineering option for stabilizing global ocean circulation. The reasoning behind the proposal is rooted in the physics of polar ocean exchange. The Arctic Ocean and the Pacific Ocean exchange water through the Bering Strait, a relatively narrow channel about 50 miles wide. Through this channel, fresh water from the Pacific flows north into the Arctic, while a smaller amount of denser Arctic water flows south. The net result is a transport of fresh water from the Pacific to the Arctic. That fresh water eventually finds its way out of the Arctic, through Fram Strait and other passages, joining the North Atlantic and contributing to the freshwater flux that the AMOC has to manage. Reducing this flux, the theory goes, would reduce one of the stresses on the AMOC. A dam at the Bering Strait could block or modulate this freshwater flow, helping stabilize the conveyor. The proposal includes various engineering options: a solid dam blocking most flow, a controlled dam with adjustable gates, an underwater barrier that disrupts the flow without entirely blocking it. The team modeled the effects of each option on global ocean circulation and found that, under some configurations, the AMOC could be measurably stabilized. The proposal has critics, many of them. The first criticism is feasibility. Building any structure across the Bering Strait would be a civil engineering project of unprecedented scale. The strait is shallow but cold, ice-covered for much of the year, and located between two countries with deeply complicated relations. Russia and the United States would both need to cooperate to build such a structure, then jointly operate it for decades. Given the current state of US-Russian relations, the political feasibility is essentially zero. The second criticism is unintended consequences. Modifying flow through the Bering Strait would affect Arctic climate, Arctic fisheries, Arctic ice cover, and biological exchange between the Pacific and Arctic. The Arctic ecosystem is already under enormous stress from warming. Adding a major engineered intervention could trigger cascading effects that nobody fully anticipates. Marine biologists have pointed out that the strait is a migratory corridor for many species, including whales, fish, and seabirds. A barrier could disrupt entire ecosystems. The third criticism is moral hazard. Even discussing geoengineering options, some critics argue can reduce political will for emissions reductions. If people believe humanity can engineer its way out of climate change, they may be less willing to make the hard choices needed to actually reduce emissions. The AMOC Dam, in this view, is exactly the kind of seductive technical fix that distracts from the underlying problem. The fourth criticism is timing. Even if the political and engineering challenges could be overcome, building a Bering Strait dam would take decades. The AMOC's potential tipping window may not allow for that. By the time the dam was operational, the threshold might already be crossed. Despite all the criticisms, the paper has had a useful effect. It has put a marker on the spectrum of possible interventions. It has forced policy discussions to include geoengineering as a serious consideration, even if specific proposals like the Bering Strait Dam remain implausible. It has highlighted just how desperate some scientists are becoming about the AMOC's trajectory. Other geoengineering proposals exist. Ocean alkalinization, where chemicals are added to ocean water to increase its capacity to absorb carbon dioxide. Stratospheric aerosol injection, where particles are released into the upper atmosphere to reflect sunlight and cool the planet. Ion fertilization of oceans to stimulate plankton blooms, and carbon uptake. Each has its own scientific basis, its own proposed mechanism, its own set of risks and uncertainties. The geoengineering conversation reflects a sobering recognition. Conventional climate policy, emissions reductions, energy transitions, adaptation investment is necessary but may not be sufficient to prevent AMOC tipping if the threshold is closer than the optimistic projections suggest. The Bering Strait Dam paper, regardless of its specific feasibility, marks the moment when AMOC conversations entered the territory of considering planetary-scale technical interventions. For now, however, scientists rely on a different strategy. They watch, they measure, they look for the signals that tell them where the system is heading right now. In any given week of 2026, somewhere in the world, climate scientists are checking AMOC indicators. The data streams come in continuously from satellites, ocean moorings, autonomous floats, and shipboard observations. Researchers download fresh measurements, plug them into analysis tools, and update their assessments of where the conveyor stands. A short list of the indicators currently under closest watch tells the story of where the science is now. The Gulf Stream's position at Cape Hatteras is at the top of the list. Following the 2026 Utrecht paper, oceanographers are tracking the 71.5 degrees west crossover with new urgency. Each month's satellite altimetry data is examined for signs of the abrupt Phase 2 leap. So far, the gradual northward drift continues. No leap has been observed, but the gap between the observed drift trajectory and the model's predicted leap behavior is one of the most closely watched in oceanography. The deep western boundary current strength along the western Atlantic is the second priority. The 4 monitoring arrays from the University of Miami study continue to deliver pressure, temperature, and current measurements. Each annual update is examined to see whether the decline is accelerating, leveling off, or reversing. Through 2026, the trend has remained consistent with the long-term weakening pattern. The rapid array at 26.5 degrees north remains the longest continuous AMOC measurement on Earth. Its data on integrated overturning strength continues to show variability around a slowly declining mean. Whether the decline is statistically separable from natural variability remains a question that will not be definitively answered until the early 2030s. Greenland melt rates are another key indicator. Satellite altimetry and gravity measurements track Greenland ice loss in near real time. NASA's GRACE-4 mission, the European Space Agency's Cryosat-2, and various other instruments provide ongoing measurements of how much fresh water is being released into the North Atlantic. The trend continues to be accelerating loss, with each summer's melt season setting new records on a regular basis. Sea surface temperature patterns in the North Atlantic are watched for the so-called warming hole or cold blob, a region of the subpolar Atlantic that has cooled while the rest of the planet has warmed. This anomaly is widely interpreted as a signature of AMOC weakening. the cold blob has persisted and, in some seasons, intensified. Salinity patterns across the Atlantic are tracked through the Argo float network. About 4,000 autonomous floats drift across the global ocean, periodically diving to 2,000 meters and returning to the surface, measuring temperature and salinity along the way. Their data feeds into models of where freshwater forcing is strongest and how the salinity field is evolving. Tropical Atlantic conditions are monitored for early signs of rainbelt shifts. Sea surface temperatures, rainfall patterns, and atmospheric pressure systems across West Africa are tracked for evidence of the southward migration that AMOC weakening is expected to produce. Some signals consistent with that migration have appeared, but the variability of natural year-to-year monsoon behavior makes attribution difficult. The Southern Ocean wind strength is measured through scatterometer satellites. The strength of the westerlies that drive Southern Ocean upwelling, and that may stabilize or destabilize the AMOC at the global scale, continues to be tracked. Sea level rise rates along the east coast of the United States are monitored through tide gauges and satellite altimetry. Acceleration of the regional sea level rise is one of the more direct fingerprints of AMOC weakening, and the data continues to show acceleration above the global average. Critical slowing down indicators in observed AMOC time series are being calculated by multiple research groups. Variance and autocorrelation in the observational record, when computed over rolling windows, can in principle reveal whether the system is approaching its tipping point. Different groups have produced somewhat different results, but several have reported signals consistent with approach to tipping. A handful of less conventional indicators are also being explored. Plankton population shifts, fisheries catch composition changes, coastal flooding event statistics, each provides a partial view of an AMOC-related signal, and combined analyses are starting to integrate them. The collective picture is one of vigilance. No single indicator definitively confirms that the AMOC is about to collapse. No single indicator definitively rules it out. The system is showing multiple signs of stress, all consistent with what models predict for an AMOC moving towards instability. Scientists are not yet at the point of declaring crisis, but they are at the point of treating the system as an active concern that requires continuous monitoring. While scientists watch, the cities sitting on the front line are beginning to act. Norfolk, Virginia is sinking, not in a poetic sense, in a literal one. Land subsidence combined with regional sea level rise has produced one of the fastest rates of relative sea level rise of any major United States city. The metropolitan area sits at the front line of climate adaptation in the country, and its responses to encroaching water offer a glimpse of what other coastal cities are starting to plan for. Norfolk has spent over $1.5 billion on flood mitigation infrastructure since 2010. Tide gates, pump stations, raised roads, elevated buildings, restored wetlands. The city has adopted a resilient Norfolk plan that mandates new construction be elevated above projected flood levels. Some neighborhoods are being studied for managed retreat, where residents would be bought out and the land returned to natural state. The naval base in Norfolk, the largest in the world, has been investing heavily in flood protection, because the security of the Atlantic Fleet partly depends on the base remaining operational. Charleston, South Carolina has launched a similar set of programs. The city is in the middle of a multi-year project to raise critical streets in the historic downtown above expected high tides. New buildings in flood-prone zones must be constructed with first floors above projected flood levels. Tide gates are being installed at storm drain outlets to prevent backflow during high tides. Miami Beach has installed dozens of pumps to push water out of streets during king tides. The city has raised sidewalks and roads in the most vulnerable areas. Building codes have been updated to require flood-resistant construction. Property values in the most flood-prone neighborhoods have begun to decline relative to inland areas, an early sign of market-driven retreat. New York City, after the devastation of Hurricane Sandy in 2012, embarked on one of the largest urban resilience programs in the country. The Manhattan Flood Barrier Project, the Staten Island seawall, the Rockaway Boardwalk reconstruction, all are responses to a recognition that the city's coastline is no longer reliably protected by historical norms. Boston has launched comprehensive sea level rise planning, including specific guidance for major infrastructure investments. The Logan Airport, the MBTA subway system, the Big Dig tunnels, all have been studied for vulnerability to projected sea level rise, with mitigation projects underway for the most critical assets. Across Europe, similar adaptation efforts are accelerating. The Netherlands, with its long history of living below sea level, has been studying AOMOC scenarios for years. The Delta program, the country's national water management strategy, explicitly considers AMOC weakening in its planning horizons. Dikes are being raised. Storm barriers are being upgraded. Plans for managed retreat from the most vulnerable areas are being studied, even though political support for retreat remains limited. The United Kingdom has launched the Thames Estuary 2100 Plan, a 100-year plan for managing flood risk in the Thames Estuary. The plan considers various sea level rise scenarios, including ones that account for AMOC weakening's regional contribution. The Thames Barrier, which has protected London since 1982, is being studied for replacement or augmentation under the most severe scenarios. In the Global South, adaptation efforts face much greater resource constraints. Bangladesh has invested in cyclone shelters and elevated villages, but the scale of climate-driven displacement potential there far exceeds what can be addressed through current programs. Pacific Island nations face existential threats from sea level rise that cannot be effectively adapted to. Coastal megacities in Africa and Asia are growing faster than their ability to adapt, with millions of new residents settling in low-lying areas. The disparity in adaptation capacity between rich and poor regions is one of the central justice issues of climate policy. Wealthy coastal cities can invest in defences. Poor coastal communities cannot. The same AMOC weakening that produces manageable challenges for Norfolk could produce catastrophic displacement in Dhaka. Adaptation has its limits. Even the most aggressive defences cannot indefinitely hold back rising water at unlimited rates. At some point, retreat becomes the only option. The question for many coastal cities is when that point arrives, and what it costs to prepare for it. The AMOC's trajectory will substantially shape these timelines. A slow weakening allows decades of incremental adaptation. A rapid collapse compresses the timeline to a point where adaptation becomes impossible, and only retreat remains. Which leaves the question that really sits at the center of all this: whether what is happening in the Atlantic right now is the slow weakening or the start of the rapid collapse. Stand at the edge of any coastline along the western Atlantic, the lighthouse on Cape Hatteras, a fishing pier in Norfolk, the seawall along Manhattan, the granite shore of Nova Scotia, and look out across the water. The ocean looks the same as it has looked to every observer for thousands of years. Blue, restless, apparently unchanged, but the water is moving differently now than it was 30 years ago. The Gulf Stream that once peeled away from the coast at one latitude now peels away at another. The deep current beneath has lost a measurable fraction of its strength. The sinking near Greenland has slowed. The whole vast loop that has shaped the climate of half the planet is operating at reduced capacity. None of this is visible from the shore. That invisibility is the central problem. Human civilizations are built around visible threats: volcanoes that erupt, storms that arrive, floods that rise. These threats provoke responses. They focus attention. They drive action. The AMOC's threat is the opposite of all that. It is silent, slow, hidden in measurements that only specialists can interpret. The most consequential climate change of the next century may unfold in a way that almost nobody directly perceives until the consequences become unavoidable. The question every responsible observer has to ask, given the available evidence, is which side of the threshold we sit on. The 2026 evidence, taken as a whole, paints a picture of a system that has already changed substantially from its pre-industrial state. The AMOC is weaker than it was. The Gulf Stream has moved, the deep current has slowed, the freshwater forcing from Greenland is increasing. The corrected models project further weakening through 2100, and likely beyond. Whether the observed changes amount to the early stages of a slow but recoverable adjustment, or the early stages of an irreversible collapse, cannot be definitively determined from current data. The two trajectories look similar at the beginning. They diverge later, when the slow adjustment levels off, while the irreversible collapse accelerates. We are not yet at the divergence point. We may be approaching it. We may have already passed it. Stefan Rahmstorff has used the metaphor of a person walking toward a cliff in fog. Each step looks the same as the last. The ground feels solid. The walker has no clear signal that the edge is near until they are on top of it. Climate science is increasingly reaching for this metaphor, not as a poetic device, but as a literal description of the epistemological situation. What can be said with confidence is that human-driven warming is the proximate cause of the AMOC stress. Greenhouse gas emissions warm the planet. The warming melts Greenland. The meltwater stresses the conveyor. Aggressive emissions reductions would slow the warming, slow the melt, and slow the stress on the AMOC. They would not stop the trajectory immediately, but they would extend the time available for adaptation and increase the probability that the system stays on the recoverable side of the threshold. What can also be said is that adaptation is necessary regardless. Even in the most optimistic scenarios, the AMOC will weaken further. East Coast sea level rise will continue to accelerate. European winters may become more variable. Tropical rainfall patterns will shift. Coastal infrastructure will need ongoing investment. Agricultural systems will need to adjust. Migration will increase. The world that emerges from the AMOC's 21st century will be measurably different from the world we have known. What may be said eventually is whether 2026 was the year the weakening became unmistakable to a global audience, or whether it was just another year along a long curve of accumulating change. The history is being written in real time, the data is being collected, the papers are being published, the tipping points are being approached, or perhaps already crossed. Future generations, looking back, will have the clarity that the present moment lacks. They will know whether the AMOC stabilized at a weakened but functional state, or whether it tipped into something fundamentally different. They will know whether the Gulf Stream's drift in the early 2020s was the beginning of a recoverable wobble or the early phase of a collapse. They will know what should have been done and was not. The Atlantic Ocean has just shifted again. Forecasters are on edge. The cliff is somewhere ahead, possibly close. The fog has not yet lifted. And the next step is being taken by everyone, everywhere, whether they realize it or not.